flowing differently, and not just the cesium atom is just oscillating differently.
Yeah, I'm saying you excite the movement, excites the atom, changes the oscillation. You're saying time got affected.
Well,
But
I guess
no valid reason to say that.
Well, I guess I don't really know. I'm not like
1, 2, 3,
physicist.
1,
I
2,
couldn't
3.
tell you.
No, that's
Like,
not.
it's interesting
One,
though.
one. Okay, testing audio 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, testing audio 1. Okay, looks good. Israel's plan for a wider war. Yeah, because Israel is really bored. It's got nothing better to do with its life. This is a good channel.
You were making the point that we never miss.
Mm-hmm.
Well, do we? You know, it's a hypothesis, there's evidence, you know, what kind of thing. Say, for example, we did a segment on Ken Klippenstein and noted some of his tendencies towards self-aggrandizing, guru-esque language and kind of presentation that, you know, he's going to feel corruption and whatnot. Then to see, would a sign of a potential concern be someone appearing on Steve Bannon's War Room for a friendly chat?
Oh.
So that happened, and I listened to the segment because people were like, you don't know what he said on there. Of course I'm going to listen. And that's, what do you think? Who do you think I am?
It's Chris Kavanaugh. Of course I'm going to
So I
listen.
listened to it, and it is not a
Each year, these doors... Most plane doors aren't locked. There are no keys, no sensors or passcodes to secure them. If someone wants to pull the lever, they can.
A man opened the emergency exit door and forced his way off the plane.
And yet, with 40 million flights each year, these doors are virtually never opened in flight. So why not?
It's self-preservation, surely.
Common sense.
Most people are, smart enough to not mess with that.
The real answer relies on where planes fly.
How high do planes fly, approximately?
10,000 kilometers? Or is that
No,
I think that's
no.
overshooting it. I think you'd be in space.
25,000 kilometers. That's the height of a plane flying. Is that way too low? It's too much. It's too much. Too much.
It's maybe 50, 60,000 feet. I guess that's like 10, 20 kilometers.
Too much. Bring it down. Yeah, 1,000 kilometers? 1,000 kilometers? Still space.
50,000 feet, I think.
Some of them can go up to 43,000 feet. 30,000 feet.
100 kilometers, I think, is the definition of space.
1,000 feet. Yeah. Why do they fly that high?
I don't know. Safety, I guess.
Probably to avoid collision with other aircraft and if there's high mountain ranges. I don't know when storms or weather hit.
My guess is to avoid a turbulent weather.
I think that's a decent guess.
Now, it's true that one of the benefits of flying at 30,000 feet is a smoother ride. This is high in the troposphere, the layer in which most weather occurs. So there's less turbulence and fewer storms to navigate around.
Oh, just 30? Okay.
This is not the main reason that planes fly so high. The bigger reason, of course, is money.
As you go up, the density of air decreases, and at 33,000 feet or 10 kilometers, the density of air is just a third of what it is at sea level. So flying at this altitude, the plane runs into a third of the air molecules it would closer to the ground. That means the plane can fly about 73% faster for the same amount of thrust. And as a result, you get to your destination faster, and since you spend less time in the air, you burn less fuel. It seems in a way that climbing is wasted energy. Can you compare the descent to the ascent? Do you essentially get the energy back as you fall down the other side?
Yeah. When we climb, we burn about 80 kilos per minute. In cruise, we burn about 40 kilos per minute. And in descent, it's maybe 10. So it's almost negligible.
Not only that, jet engines are more efficient at altitude. They work by compressing air at the intake, mixing it with fuel, and igniting it. So the combustion products are ejected very fast from the exhaust nozzle. Now, this process is more efficient the colder the air is.
And at altitude, the temperature is around minus 50 degrees Celsius, which is a lot colder than an average of plus 15 here at the ground.
So flying higher means you burn less fuel for less time and avoid the weather and associated turbulence of lower altitudes.
The other reason
it's actually cheaper to fly than to ride a train. I think train is 72 cents a kilometer or something, or a mile, and a plane is 12 cents. Actually, flying is the most efficient way to travel.
and you want to fly high is to take advantage of the jet stream tailwinds. And the company likes people to do that because you're burning less fuel, so it's less money.
But there is a problem with flying this high. The air up there is unbreathable.
If you were suddenly teleported to the top of Mount Everest, a height lower than planes fly, you would remain conscious for only about 3 minutes. This is because in addition to density dropping with altitude, so does air pressure. Air pressure actually falls off faster because it depends on the weight of all the air above you. So at 10 kilometers, the air pressure is only a quarter of what it is at sea level. To be clear, the air is still 21% oxygen, but the partial pressure of oxygen, the pressure exerted solely by oxygen molecules, is around 5.5 kilopascals, which is a quarter of what it is on the ground. Now, at this pressure, not enough oxygen molecules can force their way into your blood in your lungs. To function normally, humans need an oxygen partial pressure of at least 16 kilopascals. So all the cabins of airplanes that cruise at high altitude must be pressurized. A little bit of air is continuously brought into the cabin from outside. It actually comes in.
Pressurizing the cabin makes it stronger. So I think it's part of the design.
From the compression stage of the jet engines. That is what maintains breathable air inside the plane.
The downside is that you are taking away a little bit of the efficiency of the engines.
Now, pressurizing the cabin required a radical redesign of aircraft.
Before pressurization, planes would fly up to 10,000 feet, or around 3 kilometers, where the partial pressure of oxygen is 15 kilopascals, just at the limit of what people can handle. On these planes, doors opened outward, and there wasn't much concern about the seal around them, since the pressure was the same on both sides. But once planes were pressurized, all the doors were changed to be the shape of a plug. They're wider on the inside than the outside. That way, the higher pressure inside the cabin pushes the door into its frame, creating an airtight seal. How airtight is a cabin?
It's pretty airtight, but not completely airtight. So you'll notice, for example, every time that someone flushes the toilet, you'll see some of the air pressure go down. So every time that happens, you can actually see the cabin altitude jump a little bit.
And this is why plane doors and emergency exit doors don't need locks. The difference in pressure between the pressurized cabin and the low pressure exterior is so great that no one is strong enough to pull the door inwards.
And if someone had come up and turned that while you're mid-flight?
Nothing.
Even modern plane doors that open outward are shaped like plugs. They're just cleverly designed. The main passenger door on a Boeing 737 is both wider and taller than the frame it needs to pass through. But when you pull the lever, gates at the top and bottom fold in, reducing the height just enough. However, the sides are still too wide, so the door first has to pop inside and rotate. It's that movement inwards that is impossible at altitude. It would require a force equivalent to lifting 9,000 kilograms. And airplane cabins aren't even fully pressurized to the sea level pressure of 101.3 kilopascals. You may have noticed this if you take a bag of chips on a plane. It's easy to squish on the ground, but as the plane climbs, the pressure in the cabin drops and the chip bag seems to inflate like a balloon. I measured the pressure in my plane, and at cruising altitude, the pressure dropped to 77 kilopascals, meaning the partial pressure of oxygen was only 16 kilopascals, the minimum required for people on a plane to feel normal. This has some unintended consequences.
Do you think you fart more in a plane?
If I did, I'd blame someone else. I feel like no.
No, I can't live no one alone. Do you think you fart more in a plane than on the ground?
100%. No hesitation. So it's got to do with the cabin pressure, right? So as you go up, that cavity in here now expands, and the air wants to go somewhere. And the quickest place it can go is south. Bag of chips just popped by itself.
Now, the International Space Station is pressurized to sea level pressure, 101.3 kilopascals.
So why are planes pressurized to the minimum extent possible to carry human passengers? Well, it's actually for a very good reason.
In 1988, Aloha Airlines 243 was en route from Hilo to Honolulu, Hawaii. The cabin was being pressurized as we described, but unfortunately, this plane's fuselage had a small crack. And all of a sudden, at 24,000 feet, the crack widened, and the whole roof tore off the front of the plane. Miraculously, the pilots were able to land safely, and only one person was killed. The difference between the International Space Station and a plane is that the ISS was pressurized once, and it stays pressurized.
But a plane experiences a pressure difference every time it climbs to cruising altitude. So the fuselage is stretched and then relaxed with every flight. Stretched and relaxed, stretched and relaxed.
The Aloha Airlines plane had the second highest 737 flight cycle count in the world, with nearly 90,000 in total. That's way more than it was designed for.
This led to fatigue, cracking, corrosion, and the eventual explosive decompression.
So planes are pressurized to the least extent possible to minimize stresses and extend the life of the plane. But even 75% of atmospheric pressure should be plenty to prevent the doors from opening. So how did this happen in May 2023?
The passenger panicked and actually managed to open an Airbus emergency exit in flight. They were on final approach and were quite close to the ground. So the pressure
They did it close to the ground.
differential was very little. And because of him using all of his force, he actually managed to get the door open, which was crazy. And we didn't think that was possible. But if you want something bad enough, I guess it is.
Wow. Was he okay?
He was okay. Everyone was okay in that case.
That was a pretty serious mishap. So I guess the next logical question is, have any other passengers inadvertently caused a mishap by, say, forgetting to put their phone on airplane mode? When you're sitting there on the tarmac and they come on and tell you to put your phone on airplane mode, do you do it? And why do they get us to do that? What is the reason? Is there a reason?
Obviously, they wouldn't ask you to do it if it wasn't for some benefit.
I'm unfortunately a bit of a rebel and I don't follow the rules. And yeah.
You're not worried about taking the plane down?
I make sure my parents have the airplane mode on so I can have it off.
I mean, yes, I do, because I don't want it interfering with, like, the radio or whatever.
Well, I think it's the communication interference.
I feel like I've always been told, like, it messes up, like, instruments. Honestly, they're always just told to do it. So, you know, put your phone on airplane mode.
In 1961, the Federal Aviation Administration, or FAA, found that some portable FM radios could interfere with plane navigation systems since they used neighboring radio bands. And out of caution, they banned almost all personal electronics on flights. But airlines could test any device for interference and overrule the FAA ban to allow it on board. Any device that is, except a phone. Because another organization has jurisdiction over phones, and that's the Federal Communications Commission, or FCC. See, a phone on the ground with buildings and hills around it can usually only see 1 or 2 cell towers at the same time. But from the air, it could see 10 or 20 or more. The concern was that 200 phones traveling at 800 kilometers per hour in a plane could rapidly connect to many towers at once, overloading the infrastructure. At least that's what the FCC thought could happen. So they banned cell phone use in flight in 1991. But there's a problem with this theory. A plane is a big metal enclosure, essentially a Faraday cage, so it should block almost all electromagnetic signals. That's why plane antennas are located on the outside. Your phone signals can only escape through the windows, which means they go horizontally out the sides of the plane, so they would have to travel long distances before reaching the ground. And the cell towers your phone is trying to connect to, well, they are tilted downwards, to collect all the signals from people walking around on the ground. So it's very hard to make a connection from the air unless you're flying really low. So phones could only conceivably disrupt ground networks during takeoff or landing, and the FCC never even tested if this was the case. In 2005, they went before Congress and said the rule banning 800 megahertz cell phone use in flight may not be needed in order to protect ground-based cellular networks.
As far as we know, a mobile phone has never caused an air accident. All airplane mode does for sure is save your battery life. So why are these rules still around?
I've been flying myself, and where I've gotten interference, when you're talking to a traffic controller, you get that, that signal. And that is because someone decided using their phone and the phone is on. Will one phone in an aircraft cause any problems? Probably not. Will 200 do something? Maybe. Rather than taking the chance of let everyone update their Twitter profile at 500 feet, rather than saying that, we're saying no, just keep them off, enjoy the Wi-Fi up at altitude, and that's it.
But airplane mode might soon be a thing of the past. The EU actually no longer requires it, and is pushing for airlines to provide 5G service on all EU flights.
So we may eliminate that inconvenience, but we still have to deal with airplane food. What do you think about airplane food? I wouldn't eat the bread rolls. That's anything I can handle. Apart from that, everything tastes like mush. It can either be very good or it can be very terrible.
Blandish, different consistency.
Do you think the food tastes as good in a plane as it would on the ground?
No.
But bad tasting food might not be all the airline's fault. See, the air that's pumped into the cabin at altitude is really dry. The Sahara Desert, for reference, has an average relative humidity of 25%. But inside an airplane cabin, it can be as low as 5%.
This can dry out your nasal passages, hindering your sense of smell and therefore taste. The lower cabin pressure can also decrease sensations like the intensity of salt and sugar. But there's one flavor that appears to be enhanced in flight. What do you drink in an airplane? What's your drink of choice? Apple juice. Apple juice. Yeah. Interesting. I mean, Coke, that's default.
Orange or apple juice.
Gin and tonic.
Maybe a Bloody Mary if you prefer.
You're the first one today.
Really?
Yeah.
A German survey of 1,000 flyers found that more than a quarter of them ordered tomato juice in flight. And what's really weird is that
It's incredible. I always order tomato juice.
23% of those people would never drink it on the ground.
And would you drink Bloody Mary? Would that be like a...
It's so incredible. I always order tomato juice on flight. I never drink it in real life.
standard drink at the bar, or is it a special plane drink?
I only have it on planes.
So why is everyone ordering tomato juice? Well, it could be because of the noise.
A 2015 study points to the chorda tympani, a nerve that carries taste information from the tongue to the brainstem. It runs right past the eardrum, between the tiny sound-conducting bones. So loud cabin noise might unintentionally stimulate it.
This could produce an audio illusion that boosts our sense of umami, the savory taste you find in MSG, soy sauce, and, well, tomatoes.
I always drink tomato juice, and I never knew why. It just felt like my plane drink. Or like spicy tomato juice.
Yeah.
Like both of those are favorites of mine.
Yeah. So next time you're on a flight, go for something extra sweet or salty, or maybe try the tomato juice.
I feel like with how much people fly, our perspective of flying is still pretty distorted. So why is that?
Yeah. I know that we talk a lot about accidents and incidents and we dig into them really, really deep. And people might ask, why would you be doing this? Doesn't that just make people even more afraid of flying? But the fact is that this is one of the prime reasons why aviation is as safe as it is. The fact that we have hundreds of professionals that dig deep into these accidents means that we learn from them. So every flight becomes a little bit safer. That's actually a big reason that I started my channel, Mentor Pilot, in the first place. Because I promise you, the more you know, the safer you'll feel.
Do you think that climate change increases turbulence? Depends on what people think.
There is no climate change. You're welcome.
So brown dwarfs, are they stars like red dwarfs? Nope.
She's gone. I don't think she's ever coming back. So her name is Diana. Jesus Christ. Okay.
I mean, I don't. Yeah, it's not going to change it.
You're putting in the same amount of energy, but now it takes less energy to move the atom because the weight has differed through anomalous gravitational anomalies. Okay.
They're just shooting microwaves at it, and they're just waiting for the electron to change its state back and forth.
Maintains a frequency. It does change state, yes. To a higher
That's what it's doing. It goes to a higher state, and then it goes back to a lower state, and it emits a photon, and once it emits 9 billion photons or whatever, it counts that as 1 second.
Right. Yeah, so we agree on the second. We just don't agree that a gravitational anomaly would affect the measure of that when we're using oscillations to measure it.
I don't think it will.
Under less weight, it would be more free to move. That's why pressure can affect it too, because under higher pressure, it takes more energy to make this exchange, and under lower pressure, it takes less energy. So we infer it'll be different.
Yeah, so they put them all in vacuum chambers, but regardless,
that's why I'm not attacking pressure. I'm attacking gravitational anomalies and weight.
If I don't.
Okay. I still don't know what this is. I've been doing some research on what a tensor is. I still don't know what he's doing here.
Great products are built. It's not where the future is made. It is for a certain type of lifestyle, and there's nothing wrong with that lifestyle, but it's the adoration of that lifestyle and the romanticization of that lifestyle, which is, I think, completely and utterly corrupt. Utterly corrupt. J-Lord. I read Bap's Bronze Age Mindset. It was funny, but it was a grab bag. Also, have you read Robert E. Howard's Cain and the Barbarian short stories? They're very anti-monarchy, feudalism, and aristocracy. I read part of Bap's Bronze Age Mindset. I found it primarily stupid and ridiculous and uninteresting. I don't like the language. I just don't like the way he writes. I didn't like anything about it. So I didn't finish it. I got it on my Kindle. So I didn't finish it. But yeah, it's just a grab bag of, I think, emotionalistic, emotionalistic, reactionary, I don't know, diatribes, spewing. It's not a reason.
Okay, I was actually in the middle of watching. Dialect has the meaning of the metric tensor.
We have Schwarzschild coordinates, Kruskal-Shakarez coordinates, FLRW coordinates, etc. Just as with maps of the Earth, no single coordinate system can encompass the entirety of a space-time region while accurately preserving proper distances and proper times. But each can highlight or emphasize particular qualitative features about that space-time region, which may or may not be useful to the physicist. Now, every good map needs a bar scale. And as we discussed in our prior video, a metric is simply just that, a bar scale, or the mathematical object which tells us how distances on our map translate to distances in the real world. In the case of our space-time map, it tells us how coordinate distances and coordinate times
So this is a black hole.
translate to proper distances and proper times across different locations of our map. Now, you're probably used to a map having only one bar scale. But a map of something like the Earth actually requires a bar scale at every single point, since distances and areas everywhere are continuously being distorted. On this Robinson map, for instance, a centimeter interval across Greenland does not represent the same distance as a centimeter interval across equatorial Africa. Similarly,
So we need multiple bars.
on our map of spacetime, we'll need a metric or bar scale at every single spacetime point to indicate how our spacetime distance is changing across the map. This comparison is important, so we're going to reiterate it. On a regular map, a metric takes us from physical distances on the map to physical distances on the Earth at each and every point. While on a spacetime map, the metric takes us from coordinate distances on the map to spacetime distances on the spacetime manifold at each and every point. But what is spacetime distance exactly? Well,
This is the incorrect analogy. You should show a wave.
it's more properly termed the spacetime interval, and it corresponds to the amount of time that would elapse on a clock located at a particular spacetime point, as measured by an observer also located there. So essentially, our spacetime metric tells us how fast or slow clocks all across the universe are ticking with respect to our map user's local reference clock. But since the spacetime interval contains information not just about how time is changing across the map, but also about how space is changing too, if you want to keep all this information separate, you're going to need more than just one number at each point on your map. In fact, you're going to need 10 numbers at each point. And this is where the tensor part comes in. How exactly? Well, in our last video, we explored the basic topological procedure for going from a curved surface to a flat surface, or vice versa. Basically, you cut your surface, or manifold, into many small, nearly flat pieces. Then you stretch and or skew each piece before rearranging all the pieces into a new surface. Because this process takes a distance element that is a right triangle and turns it into a distance element that is an acute or obtuse triangle, your distance goes from being described by the Pythagorean theorem to being described by the law of cosines, or one of its higher dimensional analogs. The components of the metric tensor are then just the various lengths and cosines of angles needed to determine the length of your new distance element. As an example of this overall process, let's take a look at an equirectangular projection of the Earth. This projection takes the Earth's lines of latitude and longitude and gives them equal spacing on a flat map, thus forming a standard Cartesian coordinate grid. Let's designate our axes by the variables x and y. The values of y range from 0 to pi, and the values of x range from 0 to 2 pi. Okay, now that we have our flat surface, let's follow the basic topological procedure for transforming it into a curved surface. First, let's cut the map into many tiny squares. Next, let's...
1 second. Gotta go get more gum.
Let's impose the following metric on each square. This metric, or more precisely, the metric tensor which we are assigning to each tiny square piece, has 3 numbers, or components. The first component tells us by what amount to stretch or shrink the x length of the piece. The value of this component is the sign of the value corresponding to the y coordinate of that piece. So this tells us that the x length of pieces near the equator, where the sign of the y coordinate value is equal to nearly 1, will not be stretched or shrunk, whereas the x length of pieces near the poles, where the sign of the y coordinate is equal to nearly 0, will be shrunk to close to 0. Meanwhile, the x lengths of all the pieces in between will be shrunk an intermediate amount. Now, the second component tells us how much to stretch or shrink the y length of the piece. Here, everywhere on the map, that component is equal to 1, so this tells us that the y length of all our pieces remains unchanged. Finally, our third number, or component, is 0. This tells us that the cosine of the new angle between our transformed axes should be 0. The cosine of 90 degrees is 0, and since the old angle between the axes of our pieces was already 90 degrees, this means there will be no skewing of any of our pieces across the map. we see we now have all the correctly sized pieces of a new surface. With a little more information about the coordinate transformation, we can rearrange our pieces into a new surface. Notice that there are some gaps between pieces, as well as some places where the pieces overlap and are touching, which we see especially towards the poles. This is because we did not cut our map into small enough pieces. But the theory of differential geometry assures us that, if our pieces were infinitesimally sized, the surface of the sphere will approach its proper shape and area. Now, rather than an equirectangular projection, if you instead started with a projection like the Robinson one, where the lines of latitude and longitude didn't intersect at right angles, you would end up with the third component in your metric tensor being non-zero. This would indicate that, in addition to needing to be stretched or shrunk, pieces across the map would need to also be skewed before being rearranged into their new surface. Zooming into the spot in North America, for instance, we see that the angle between the lines of latitude and longitude here is about 45 degrees. The tiny square patch which resides there then would have to be skewed until the proper angle of 90 degrees between the lines of longitude and latitude was reached. Thus, the original coordinate angle between the x and y axes on your patch, which was 90 degrees, would get stretched to a value greater than 90 degrees. And it's the cosine of that angle which essentially gives you the value of your third metric component, with the caveat that it has to be multiplied by the magnitude of the other two components first. All right, we've mastered the two-dimensional metric. So let's take it to the next level and look at a three-dimensional metric. Now, as with our two-dimensional case, we're going to start out with a flat surface for our map, which in 3 dimensions is just your conventional Euclidean 3D space. Previously, we cut our map into many tiny squares. Now, we'll cut our map into many tiny infinitesimally sized cubes, dx by dy by dz. Then we'll assign a metric tensor to each infinitesimal cube on the map. Okay, let's zoom in on a particular cube. In 3 dimensions, the metric tensor has 6 components. 3 for the 3 sides of the cube, plus another 3 for the 3 angles between pairs of axes. These components at any point will be a function of the map coordinates. Since again, our bar scale is changing across different points of the map. So let's just say that those functions, at this specific point where our cube of interest is located, end up giving us something like these numbers. Now, the first instruction from the metric tensor at this point is to multiply dx by 1.5 each infinitesimal cube on the map. Okay, let's zoom in on a particular cube. In 3 dimensions, the metric tensor has 6 components. 3 for the 3 sides of the cube, plus another 3 for the 3 angles between pairs of axes. These components at any point will be a function of the map coordinates. Since again, our bar scale is changing across different points of the map. So let's just say that those functions, at this specific point where our cube of interest is located, end up giving us something like these numbers. Now, the first instruction from the metric tensor at this point is to multiply dx by 1.5. The second instruction is to multiply dy by 3/5. The third instruction is to multiply dz by 4/5. Next, the fourth instruction is to take the angle between the x and y axes and shrink it until it equals 70 degrees. Similarly, the fifth and sixth instructions tell us to make the angle between the x and z axes equal to 80 degrees, and the angle between the y and z axes equal to 60 degrees. We now have the correctly sized piece that belongs to our new curved manifold. Moving to the next point in our 3-dimensional map, we read the new metric tensor instructions there to size that piece as well. Repeating this for every point in our 3D map, we arrive at a collection of properly sized pieces for our new manifold. Now, were we in possession of a higher dimensional coordinate transformation, we could conjoin these pieces into a curved entirety like we did with the Earth. However, there's a problem with this. The problem isn't that we can't imagine more than 3 dimensions. Rather, it's that we may simply not be in possession of a higher dimensional coordinate transformation to begin with. And backwards deducing one may not be possible or physically meaningful. At any rate, if our map is equipped with a metric tensor field, we will at least have an understanding of how the manifold looks locally at every point. Well, that's it. You're just steps away from taking the metric tensor into the 4 dimensions of space-time and beginning to really understand how general relativity works. But we're out of time for today, so we'll continue our exploration of the meaning of the metric tensor in a future video. So stay tuned. This has been Dialect. Thanks for watching. We're often told in physics that the presence of massive bodies warps the fabric of space and time. But what does such a statement actually mean? Most visuals are heuristic tools that don't offer clear understanding, leaving one to wonder, is it possible to actually visualize space-time curvature, especially near an object so massive we can cross a limit of no return? This is Dialect with the geometry of a black hole. What does the curvature of space and time around a massive body actually look like? To answer this question, we need to turn to a mathematical object called the Schwarzschild metric. Presented in tensor form, this metric is a matrix with 4 expressions along its diagonal components. Now, in our prior videos, we demonstrated how the components of a metric tensor can be interpreted as instructions for resizing infinitesimal pieces of a map in order to fit those pieces to a curved surface. And indeed, this is the case whether your map is one of a physical surface like that of the Earth, or whether it's a map of a more abstract surface like that of the space-time manifold. We can thus use the Schwarzschild metric to construct for ourselves a model of curved space-time. But first, we must get our hands on the map which the metric belongs to. Here, we turn to what's formerly known as the Schwarzschild coordinate chart. This map depicts space-time in the vicinity of a single, centrally located, non-rotating, uncharged spherical mass. Now, just as there's no one right way to map out the curved surface of the Earth onto a 2-dimensional Cartesian grid, there's no one right way to map out the curved surface of space-time onto a 4-dimensional Cartesian grid. Consequently, we have a choice in how to make such a projection. Motivated by the spherical symmetry of the region, the Schwarzschild approach is to assign to every world event that occurs a set of more or less spherical-like coordinates, t, r, theta, and phi. The first coordinate, t, is intended to be analogous to a traditional time coordinate. As there is no global time in this region, and clocks everywhere tick at different rates, the simplest solution for describing time here is simply to choose a master clock, meaning a clock against which all others can be compared. The natural choice will be that of a clock belonging to a distant observer, since, far out from the central mass, space-time curvature will be negligible. All events which transpire across the space-time region are thus assigned a time coordinate based on whenever this distant observer perceives them to occur.
Hello? Hey, do you know GR?
Talking about is from there. You don't know medicinal mass media? It's a server that's kind of like this one.
No, I don't know. Do you know physics?
No, I don't. I'm bad at math. I'm lazy at math. I'm just really good at English. Math is a language, but you got to look up stuff to be good at math and study. English just comes really easy to me, and languages in general. You know what I mean about math, especially physics. It's not like 1, 2, 3.
Are you good?
You know what I mean? Yeah, I'm not good at math because there's a lot of studying you got to do, and a lot of practice. But for some reason, like languages that are like, I don't know, text based. Now, math is a numerical based language. I don't know. Physics probably has words. Maybe.
Mm-hmm.
Yeah, of course it has words. I don't know. You left, bro? Where you at?
No, I'm thinking if...
Oh, you there?
Yeah, I'm here. I'm just thinking maybe you're good at math, you just don't know that.
Yeah, I know. I have potential in every subject or any category, everything that exists. I have potential. I just don't practice at it. But for some reason, I guess I practice at English. I don't know.
The question is, can you imagine like 3D? Can you imagine things? Can you imagine objects falling and like stuff like that?
Yeah, I mean, you mean like theories? Yeah, that's English. That's language.
No, but can you imagine things? Can you build things in your mind? Can you imagine?
I guess so. well, not like I don't know, like making algorithms or what you call the equations. I don't know how physics works exactly, what the word is, but not mathematically create things. That's what you're trying to get at?
No, like if I told you to design your house, would you be able to imagine the house? Would you be able to?
Yeah, but I wouldn't know the specifics of like the products, or what do you call it? The what you call it? The things that make up a house exactly, like I beams or whatever. But I can have a basic idea about how to make a house. I just don't know like the names of all the supplies. That's the right word, supplies.
No, but would you be able to imagine if I told you close your
Yeah, I
eyes?
can have a concept of a house. Yeah, and think about it in my head, my ideal dream house. Yeah, can do that. I just can't do it in real life. Actually, build a house all by myself. There's some people that could do that. Let's go at it like that.
Mm-hmm.
Especially carpenters.
Mm-hmm. Hold on one second, Jerry. Are you here?
Yeah, he's here, but he's muted. He muted his mic.
What's up?
Oh, what's up, Jerry?
Hey,
Do
what's
you?
up, you silly Jerry?
Jerry,
What?
what's going on, man?
Hey, Jerry. Do you know physics?
No.
This shit is hard, man. That's a hard math.
Hmm.
I bet it is. It's not. It's not arithmetic. It's high level. It's not your times table. It's like comparing English to Japanese or Chinese. They're languages, but they're complex as heck. There's like a million different words that meanings for one simple word in Japanese alone. Chinese the same way too. And English only has like 20 something letters, but Japanese, you need to know 1945 to be fluent in writing.
Hmm.
That's how complex that language is. Just to be fluent in reading and writing. 1945. Why do you think they're so good at that coding and everything in that country and technology? English like a toy to them. Sorry.
Yeah. I gotta go. I'll see you later.
That sharp British tone, you know.
Yeah, but read the experiment. Like it was pretty, like a nanosecond here, a nanosecond there.
Yeah, you break it down the billionth of a second, man. That's real minuscule, and a lot of things could cause that.
And they
How
got
do you
different
time a
readings when
billionth
they
of
were
a
going.
second?
Yeah.
He tried to hyper glorify it, hyperinflate it by calling it an exact measurement. No measurement's exact. We all know that. That's why it's laughable.
If I just shake the rock, will it will it tell you time doing something?
If you
Then
shake
if I
the clock,
shock
you'll
it,
probably fuck it all up, and we'll have to recalibrate it. It's an atomic clock.
right?
You just can't do that shit to an atomic clock, bro.
Yeah, it's gonna tell you I
They're
went
too
to the past
sensitive.
before. Right.
The temperature in your front room, if you got it in your front room, the temperature change can affect the time. So
Yeah, so you're not shaking a rock, you're applying electricity to crystals and see how often it
a jet plane vibrates
Kinetic
and
energy,
shakes,
it's
doesn't
all-
it,
yeah.
Matt?
It's
You
all.
put it on.
It's
You
all.
put these on planes, man. They're vibrating, shaking. They got jet engines hooked up to them. Cutting through the atmosphere, the temperature changes. The cabin pressure is constant, but so did they set them in there and then get the cabin pressure constant and keep it all constant, and then actually zero out every clock again and make sure they're
I'm
still
glad you asked there, Mike. Look, like you can tell I've done this before, right? Look how they brought them up in the plane. Check it out.
Bro, that's what I'm saying, man. All the shit involved in this could have affected the accuracy of this clock. Did anybody even consider to zero the thing out and calibrate it once it was placed in there, in the jet? And where's the vacuum chamber this was supposed to be in that Kushal was talking about, bro?
It's inside. The tube is inside that box.
Yeah, the
believe it or
clock
not.
has a vacuum tube inside it. Yeah, I know that. Everything. So the oscillations, we put them in a tube and input energy, and we keep it at a high level oscillation. So if you affect the delivery of energy, the weight of the atom, the temperature of the atom, the pressure acting on the atom, any of these things can make a billionth off. Now you're going from what ceiling did they fly to? 10,000 foot, 30,000 foot. There's a pressure change. Plus we're in motion. These are two things that can affect it. I guarantee there's going to be a temperature change.
Guys, can I ask maybe a question? Does anybody here know GR? Like general GR, general relativity.
GR, general relativity.
We're actually talking about the two clocks, the atomic clocks and time dilation proof on GR right now. You're going to ask if we know it?
Okay, so my question is,
Make your postulation.
my question is, if you have two clocks, if I have a clock as I'm sitting on Earth, one clock is on my desk.
Holy shit.
Listen, I think my boy C. Montreal is already ready for you. We just covered this argument. We're coming to the tail end of it, but if you want us to go back through it, I'll let either Jeremy or C. Montreal do it for you.
Anyway, so my question is, I have one clock on my desk, another clock I drop from my desk. So one is falling right from my desk and one is on my desk. Which one is ticking faster, do you think? Again, one is sitting on my desk and one is...
How's the desk? What size clock we talking about?
What do you mean?
Because one's about to be broke.
Yeah, but as it's falling, as it's falling compared to the one sitting on my desk, which one is ticking faster?
I don't see any reason why they wouldn't tick
Who
simultaneously.
fucking cares? Who cares? It doesn't have nothing to do with time. You're talking about about a damn clock.
No, this is
Yeah,
general.
let's stay on
Silly.
topic there, buddy. Let's not just come in and just take over the show. Like we're talking about a certain thing.
Oh,
you don't mind, like stay
I'm
on
sorry.
topic, please.
Oh, I didn't know. I'm sorry.
Well, I'd say from the desk to the floor, that ball is not going to change anything. They'll tick in unison so the clock.
Big hypothetical. What if?
Yeah.
But
Why don't we just use a digital clock and then solve that problem for everybody, and then it'll be the same time?
Demark it. Demark it.
All right, we can do that.
No, my question is about GR. Assuming GR in GR.
Come on, man. You got to hang in there a second, there, bro. Hold on.
He's saying we got to add in a length contraction, bro. You caught that, right? See, Montreal. You got to add in that length contraction.
Yeah. Look, we can change topics if you like, but I mean, it's up to you guys.
Love to.
Okay, what do you got?
What do you got?
Oh shit! Now I want to stop.
Come on, man.
Yeah.
You're up on bats now.
Don't be a Mongo, man. Don't
All
be a
right. All right. No Mongo. All right.
No Mongo.
All right. Fuck. Coriolis. Shit.
Oh man. Really?
Anyway, this would be an interesting question. I don't know, like if somebody who knows GR, would they be able to quickly answer? Because according to the ether theory, so a clock on my desk has the ether flowing through it, so it's slow. But a clock falling, as it is falling, it's moving with the ether. So initially, as it's just starting to fall, they're ticking at the same rate. There's no difference between falling and not falling. There's no difference. Just the fact that you're falling That doesn't change the ticking of the clock. At that instant that you're starting to fall, that's that doesn't change the ticking of the clock. It's only the motion through the ether as you're beginning to pick up speed. It's only that that changes the rate of your ticking. So there's different predictions. Therefore, I think I don't know what GR says. Yeah, I need to study GR. This is the reason why I'm studying GR, because I don't know what GR says.
The second coordinate, r, is analogous to a radial coordinate. It is produced by placing observers in concentric rings about the mass, then having those observers measure the circumferences of the rings, in order to deduce, via dividing by 2 pi, what the respective radii of the rings would be, were the overall geometry of the space-time region there flat. This is like making a bird's eye map of a circularly symmetric hill. The radial distance between any points and the top of the hill obviously depends on the hill's curvature and grade. But once projected onto a flat surface, this distance instead becomes the circumference of the contour which the point occupies, divided by 2 pi. Meanwhile, the third and fourth coordinates, theta and phi, retain their ordinary meaning.
I have to listen to this again. U.S. bankrupt. The extreme right and left, they can't wait for the U.S. to become bankrupt. Oh, they're licking their lips. Oh, the U.S. must go bankrupt. Meanwhile, the U.S. economy is is blowing all the other economies out of the water. The world is going to hell, and the U.S. is thriving. Lex Friedman. Oh my God, what a joke. I love everybody. I love everybody. I am Jesus. I am Jesus. I love everybody. I love you so much. Meanwhile, he blocks everybody on Twitter. I love everybody so much. I am the best person in the world. I love everybody so much. This guy used to be right wing, and now he's extreme left wing. La la la. Hello. Serious. What's up?
Hey.
Hey.
Hey, what's your Discord about? Somebody linked me to it, and I've never been here.
It's about anything, but like I like doing physics and science. Like anything that has to do with smarts. Like I'm not into any conspiracy theories.
You're not into conspiracy theories?
Theoretically, I'm not, but I guess I am. Like, I'm anti big physics. I think pharma is good, but I'm anti COVID. I don't believe there's global warming, but I don't think there's a conspiracy. I think there's just it's more like, so is COVID. I mean, there's no conspiracy of COVID. I think there's just confusion around COVID. There's a lot of misinformation, but not so much disinformation. It's like everybody's lying to each other, but they don't really mean to lie. They're not really aware that they're lying. like the people that believe in COVID, I don't think they know they're lying.
Right.
Anyway, what's your opinion?
Yeah, I don't think they know. I mean, they believe what they believe, even though they may believe something false. That's what they believe is true.
Right. It's like people who believe like in religion. People that believe in a religion, they really believe it. Even though, everybody else that doesn't believe that religion, they know it's false.
Mm-hmm.
So like I'm an atheist, so I believe that anyone who believes in a religion is wrong. But I don't think they're lying. I don't think they know they're wrong. But if you really talk to them about it, at one point they'll admit that it's a lie. And like if you debate, like if somebody believes in COVID and you debate them, at one point they're going to say, "Well, I trust the science," meaning
Right.
they don't know the facts, so they just don't know. So they're lying when
You
they.
don't stream. I'm sorry to interrupt. You don't stream your Discord, do you?
Yes, I do.
Oh, like right. You're not doing it now, are you?
Yeah, actually, I am.
Oh, I got to get off then. I don't do that.
Oh, okay. Why? Oh my god. Oh my god. Wow, people are terrified. La 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 la. Even on my server, people are terrified of being streamed. Anyway, what's the best way to study tensors? Because I've been studying this guy, but I don't know. I don't know. I mean, there's so much more to go, and I'm just becoming more confused.
Tensors. In the last video, we covered forward and backward transformations, and in this video, we're going to talk about our first example of a tensor, which is the vector. So what is a vector exactly? Much like tensors, you might get different answers to that question depending on who you ask. So this is one definition you might hear. A vector is a list of numbers, or a vector is a one-dimensional array of numbers. So that's a nice, easy definition. And here are a couple examples of vectors, v and w, and they're just lists of numbers. So you probably already know, if we want to add these lists together, we just add them like this, right? We just add the corresponding elements to get the new vector with elements v1 plus w1, v2 plus w2, and so on and so forth. So that's vector addition with lists. And you probably also know that we can scale vectors using a scaling constant like this. So all right, welcome to this video.
Let me just mark each of the videos.
All right, so welcome to this second video in my series on tensors. Welcome to this first real video in my series on tensors. Welcome back to the video series on tensors. In the last video, so in the previous video, I left off with this. In the last couple of videos, we saw our first example of. So we're continuing with our discussion of covectors. In this video, we're going to talk about covector components. So just a quick review, we said that covectors are functions that take vectors to produce numbers. These functions are linear and obey these properties here. These functions can be added and scaled in a meaningful way, and because of that, they form a vector space, which we call V star. In the last video, we saw that all covectors can be written as linear combinations of the dual. So we're continuing with our discussion of covectors. In this video, we're going to talk about covector components. So just a quick review, we said that covectors are functions that take vectors to produce numbers. These functions are linear and obey these properties here. These functions can be added and scaled in a meaningful way, and because of that, they form a vector space, which we call V star. And finally, we can visualize covectors as these oriented stacks of planes. So when I first introduced covectors, I said that they were a bit like row vectors. So we know that a column vector really represents a vector's components in a given basis, right? So that makes you think that row vectors somehow represent a covector's components, and that's exactly correct. So I'd just like to pause here and state this in case it's not already obvious. Covectors, like vectors, are invariant. They are purely geometric objects, and they do not depend on a coordinate system. But covector components do depend on the coordinate system. So covector will be represented by different row vectors with different components depending on which coordinate system we're using. All right, so that aside, what do we even mean when we say that a covector has components? When we write the column vector 2, 1 in reference to a basis here, what we really mean is that this vector is given by the linear combination 2e1 plus 1e2. We're just telling you how much of each basis.
Okay, so when we write, so this is a covector, because until now I think it was rows, so now it's a column. So this is 2, 1. He said it's a covector. Let me hear it again.
Depending on which coordinate system we're using. All right, so that aside, what do we even mean when we say that a covector has components? When we write the column vector 2, 1 in reference to a basis here.
Okay, so this is a column vector. It's not a covector. Wait, is a column vector a covector? Anyway, so this is a column vector. 2, 1 in the E in the in the original, this is called the original. There's the old and the new. So the new is the tilde. This is the old. So in the old coordinates, this is 2, 1, which just means 2e1 plus 1e2. Okay.
Here, what we really mean is that this vector is given by the linear combination 2e1 plus 1e2. We're just telling you how much of each basis vector is needed to make.
So if we have x and y, oh wait, this is e1 and e2. So this is just 2 and 1. So it's this vector. Okay.
The vector. So what are we talking about when we say a row vector 2, 1? Like 2 of what and 1 of what? So remember.
So this is now it's a row vector. So what exactly are we measure with when we write 2, 1? I think he wrote comments that there's many issues, errors. Throughout the video, the spacing for the epsilon covectors, okay, in the diagrams is wrong. See this. Okay, I don't think we got to this point. This is the tildes. So we're going to get to the tildes. This is the beginning of curvature. You can already see the topology being how the tensor is related to the topology, how it describes a topology. Anyway, we'll get to 619 and 753. Okay. So what exactly are we measure with when we write to, I don't know, what is he saying here? What exactly, I guess, what do we mean? He said, what do we mean?
Basis vector is needed to make the vector. So what are we talking about when we say a row vector 2, 1? Like 2 of what and 1 of what?
I would say it's the same, isn't it? I mean, why would it be any different?
So remember, covectors are functions from the vector space V to numbers. Covectors don't live in the vector space V, right? They take vectors in V as inputs. So we can't use basis vectors in V to construct covectors. So what do we do? Well, what we're going to do is work V, right?
So
they take vectors in V as inputs. So we can't use
So covectors, I guess 2, 1 row vector is a covector, are functions alpha such that they map a vector to a real number. Well, this is a covector. Covectors don't live in the vector space V. Well, I guess this is the vector space E, E1, and E2. We use Kant basis vectors. Oh my God. I guess we can't use basis vectors in V like E1, E2 to measure covectors.
Basis vectors in V to construct covectors. So what do we do? Well, what we're going to do is we're going to take a basis E.
So his notes are completely messed up. Anyway, take the basis E1, E2 for V.
1, E2 for V, and we're going to introduce two special covectors, epsilon 1 and epsilon 2, which are both functions from vectors to numbers. And you'll notice
there's two spatial. Is this spatial or special? I think this is special. Covectors epsilon 1, epsilon 2 that map V to a real number. So given E1, which is the component, well, there's no component. This is just a basis. Epsilon is the component. So epsilon 1 is the component of E1 is equal to 1. I don't know what's going on.
Notice I put the labels 1, 2 above the covector instead of below.
Oh, because it's a covector.
Did that on purpose, and we'll get to why I did that later. Anyway, these covectors are defined as follows. When epsilon 1 acts on E1, we get 1. And when epsilon 1 acts on E2, we get 0.
I'm thinking I should write a paper that explains because in this paper Where does the apple fall? There's no gravitation time dilation. So I should just write a paper let's create a paper how we get gravitation time dilation this is ether based gravitation time dilation. How do you get gravitation time dilation? So let me go take one of the images. I'll take the last image from the ether flux paper and I'll just paste it here. Okay, let's remove some stuff. So gravitation time dilation. This is the ether. So we basically need the rubber ducky to experience the time dilation. So first we need to show how ether flow causes time dilation. So that we have in the original paper. So let's go to the last image in this paper, or the last before. So this is time, you can see the time dilation here. Yeah, these circles are good for, and the arrow, this gives you the feeling of time dilation. So we need to start from, if you move through the ether, the faster you move through the ether, the more time dilation you're experiencing. Therefore, if the ether is moving through you because of gravity, you should be experiencing just the same time dilation. There's no difference. Amazing that it's always undetectable. The way the universe works is that time dilation, you can never detect your own time dilation. That's why an interferometer can never detect the ether. So we should write a separate paper why an interferometer can never detect the ether. Let me see. Let's write another paper. New Google Docs. Why an interferometer can never detect the ether. It's not just that. It's if we assume special relativity. This is because of special relativity. This is the most incredible thing. Because assuming special relativity, why special relativity says that an interferometer can never detect in the ether. That's the most fascinating thing. What's going on? Where is he? Oh my god. So why special relativity says that an interferometer can never we need to do the oh, you can't see it. We need to do the calculations. That's actually very important. I think I need to do this before anything. Biden says discussing Israeli attack on Iran oil sites. Yeah, that's half a sentence. Israel's plan for wider war. Yeah. Israel should conquer the Middle East. I wouldn't even say because it has no choice. That's what Israel should do. Every country should seek to expand. That's the nature of the beast. Israel is the best country in the region, and the rest of the countries would benefit from the rule of Israel. And they don't leave Israel much of a choice. Look. MFG refused. Who's MFG? What is MFG? Okay. So it's really very simple. This is the most important paper. This is before anything else. So let's start with a diagram again. We'll take this diagram again. Before no. This is not a diagram. We need to do the calculation. YSR says that an interferometer can never detect the ether. So we actually need to do a calculation. So calculation. So what's the calculation? So so the interferometer should create an interference pattern I mean, we should have a delta. So we need to show the diagram. Yeah, we need to show the diagram. Okay, so this is going to be figure 1. Yeah. Why is it not working? This is going to be figure 1. This is going to be the interferometer. This is the ether flow. And this is the ether pressure. Okay, so this is going to be the table. Let's put it in the center. Let's move these away. We just need one. This can go away. All right, the ether, we'll put it away for now. Okay, so this is our device. Let's make it bigger. Difficult to tell. Let's make it. This is 4 by 4. From 1 to 4, from 1 to 4. So it's 1, 2. This is 1, 2, 3. Okay, so it's 3 by 3. So let's start from 2. Okay. Now let's assume, how do you rotate this from here? So we'll assume the ether What? Why is it not on center? Let's make it bigger. Weird. Okay, this is the ether. So the ether flows this way. So the ether causes length contraction this way. So why does the ether cause length contraction? So the ether causes time dilation. But why length contraction? So we need to study why. I never actually got around to length contraction. So time dilation is easy, but length contraction is not. Length contraction is a little bit confusing. So length contraction, let's see this.
If you're moving at a third the speed of light to my left, then in our universe, when you change from a non-moving perspective to a moving one, or vice versa, that change of perspective is represented by what's called a Lorentz transformation, which is a kind of squeeze-stretch rotation of spacetime that I've mechanically implemented with this spacetime globe. Two of the most famous implications of Lorentz transformations are phenomena called length contraction and time dilation. And while their names make them sound like they're two sides of the same coin, they're definitely not. We'll start with time dilation, which is easier to see. Suppose I have a clock with me that ticks every 2 seconds, but if you're moving at a third the speed of light to my left, then from your perspective...
You see, they don't have a mechanical explanation. This is all they can do is give you geometric predictions, but they don't give you a mechanical explanation. There's no mechanical explanation.
Perspective, the time coordinates at which my clock now ticks are slightly farther.
This is Minkowski's space. It's a tool to give you time dilation and length contraction, but it's not a mechanical explanation. It just assumes a constant, because we have a constant speed of light for all observers. Therefore, we must, to accommodate the fact that that the speed of light is constant, to accommodate that postulate, therefore these things must be true. But there's no mechanism. It's not mechanical.
Apart. According to you, it takes about 2.12 seconds.
So these people, they don't feel like they live in a magical universe.
Between each tick, instead of 2 seconds. Time literally is running slower for me relative to you, because Lorentz transformations, which represent how relative motion works in our universe, kind of stretch things out.
Works in our universe. That's just the law. It's a law of nature. It's just a law of nature.
Bit. Likewise, if you have a clock with you that ticks every 2 point...
And I explain this to people. Look, it comes out of the ether. Yeah, but you have to invent the ether. Where is the ether coming from? What do you mean? Where's the ether coming from? Where is it coming from? So we would rather live in a magical universe with no mechanical explanation for the constant speed of light or for gravity. I'm comfortable. I would rather live in a universe with no explanation, rather with an explanation. Jesus Christ. Yeah, I need to study time dilation and length contraction with their Minkowski space. Let's see this.
The two ends at the same time. I've spoken about special relativity for quite a few videos, and I'm going to stick with that subject matter here too. The last handful have focused on relativity basics and how clocks tick differently for different observers. But there's another counter
with no explanation for why that happens. It's just, it must happen because everyone observes a constant speed of light.
Intuitive consequence of relativity that confuses the heck out of people. This is the idea that different people see lengths differently. I mean, how can that possibly be? I bet you know that I'm going to tell you because, well, you guys are smart that way. Before I start, I should tell you that this video has an actual derivation, uses relativity wrong, but it has something even more important. It first uses relativity wrong, but in a way that seems right. Then I identify the mistake and redo things properly. This is a super important thing to see because it's so easy to make mistakes in relativity. The good thing is that the math is pretty easy. We just start out with the standard Lorentz transform equations.
Wait, this already assumes contraction. This is length contraction.
As a reminder, those are the equations that you see here. If you've not seen them before, I talked about them in my video on what relativity is all about. Take a look at that video.
How is that possible? You're supposed to teach length contraction today, but this is length contraction.
If you like, or you can just trust me and we can press on. Remember what these two equations mean. We have two observers looking at a situation. For one of them, the situation isn't moving. For the other one, the situation is moving. Typically, we say the person seeing the situation not moving is the unprimed observer, and the moving person is the primed observer. So, in this situation, all we want to do is measure how long a stick is. Now, this just doesn't sound all that hard. I mean, like, there's a stick, and I measure how long it is, and there you go. I mean, how hard is this? Like, am I wasting your time or something? Well, I hope not, because you have some experience measuring a thing that isn't moving, but you've probably never measured the length of something moving at an appreciable.
That's true. Like, it's not simple to measure something as I'm moving. Like, if I'm not moving, it's easy. But what if I am moving?
Fraction of the speed of light. Have you?
No. It's a good point.
Well, no, of course not. Sorry, dumb question. But now, let's be a little careful about how you measure something. The way you actually do this is to find the location of one end of a stick and then the other end of the stick, and then subtract those two locations. Suppose you had a meter stick and you labeled the ends A and B. You could put end A at location 1 and the other at location 2, which we'll call x1 and x2. x1 could be at position 0. Then x2 would be at 1 meter. Subtract the two, and you find that the meter stick is indeed 1 meter long. Now, you could have picked other locations. x1 could have been at 98.3 meters, which means that x2 would be at 99.3 meters. And if you subtract those, again, you get 1 meter. Yeah, I know. All of that was painfully obvious, but trust me, it's about to get a little more mind-bending. So let's just ask ourselves what a moving observer thinks. And to do that, we're going to exploit the Lorentz transforms. I'll tell you what, let's make it more interesting and not use a meter stick, but rather some stick with an unknown length that we'll call L. Let's say that the unprimed observer, which I remind you is the one who's...
So there's prime and unprimed. The unprimed is not moving, and the primed is moving. The problem is that they're moving relative to each other. So each one calls the other prime. Okay.
Sees that the stick not moving.
So which one?
With an unknown length that we'll call L. Let's say that the unprimed observer, which
unprimed is the stationary,
to remind you is the one who sees that the stick not moving, decides to do the measurement at the
wait, the unprimed sees the stick not moving. Okay, so stationary with the stick. So I'm stationary and the stick is stationary. Okay.
Time equals 0. Suppose further that she puts one end of the stick at location 0. Then, rather obviously, the other end of the meter stick is at location equals L. Putting this in terms of x's and t's, we would say x1 t1 equals 0, 0, and x2 t2 equals L, 0.
Wait, what is the other 0? Okay, got it, yeah. x1 equals 0, t1 equals 0, x2 equals L, t2 equals 0. Okay, so times 0, this is L. Well, because she's stationary and the stick is stationary. Okay.
So let's put those into the Lorentz transform equations and see what the primed observer sees. For location 1, you get the same 0, 0. But for location 2, you get x2 equals gamma L and t2 equals gamma v.
I don't know. I have no idea why you would say any of this. You completely lost me here. What do you mean use the Lorentz? Why would you use the Lorentz? I don't understand.
E over c squared times L. Pushing ahead, you could then subtract the two x's according to the primed observer, and you'd get that the length according.
But why would you say this? I don't know. I don't want to waste my time. This is a waste of time. He's assuming Lorentz. What's the point of the length contraction and real explanation if you're assuming Lorentz?
It's not just time that behaves strangely according to special relativity, it's space as well. According to special relativity, lengths contract in the direction of motion.
My God, how gay are you?
And I'm afraid... Hello, folks, and welcome back. I'm Brian Roberts, and I'm afraid the weirdness continues. It gets weirder. It's going to keep getting weirder for some time now, so strap in. So if my spaceship is headed in some direction, and I have a ruler oriented in the same direction, then that ruler will shrink when the spaceship is set in.
Why do gay men love physics so much? Jesus.
Motion. That's called length contraction. It too is a consequence of nothing more than in motion in the same direction. So if my spaceship is headed in some direction, and I have a ruler oriented in the same direction, then that ruler will shrink when the spaceship is set in motion. That's called length contraction. It too is a consequence of nothing more than the light postulate and the principle of relativity. It's a little bit more involved to understand why it's true, but let's give it a try. For this thought experiment, we're going to take two light clocks set up perpendicular to each other. A bulb flashes and light beams are sent up along the edges of each clock where they hit a mirror and come back to the origin.
Well, this is good. This is an interferometer. Very good.
Origin again, where they meet. The two light beams return to the same place at the same.
Show a wave. Don't show a beam. Show a wave, and everything will be clear.
Same time. There's no way anybody could disagree about that. It's the same event. Now I set this apparatus in motion away again, where they meet. The two light clocks set up perpendicular to each other. A bulb flashes and light beams are sent up along the edges of each clock where they hit a mirror and come back to the origin again, where they meet. The two light beams return to the same place at the same time. There's no way anybody could disagree about that. It's the same event. Now I set this apparatus in motion along the direction of one of the light clocks. And let's make it fast, really fast. 99.5% the speed of light fast. Now, someone on the spaceship will observe these two light clocks to be behaving normally, as if they were at rest. But for someone on Earth watching this apparatus in motion...
Wait, what?
Now I set this apparatus in motion along the direction of one of the light clocks. And let's make it fast, really fast. 99.5%.
What do you set in motion? What?
Light beams are sent up along the edges of each clock where they hit a mirror and come back.
Yeah, but it's stationary.
Back to the origin again, where they meet. The two light beams return to the same place at the same time. There's no way anybody could disagree about that. It's the same event. Now I set this apparatus in motion along the direction of one of the light clocks. And let's...
What? What did you just say?
It's the same event. Now I set this apparatus in motion along the direction of one of the light clocks. And let's make it...
Okay, so this apparatus is now moving, let's say, to the right. I guess when he was speaking, he didn't have the illustration. Somebody did the illustration after.
Get fast, really fast. 99.5% the speed of light fast. Now, someone on the spaceship will observe these two light clocks.
Relative to whom?
To be behaving normally, as if they were at rest. But for someone on Earth watching this apparatus in motion, a strange thing will happen. Think about that light clock that's oriented in the direction of motion. The light beam leaves the bulb and heads out towards the mirror in a hurry. But that mirror is moving fast. It's moving at 99.5% the speed of light. So although the light beam travels faster, it travels at the speed of light, it has a lot farther distance to travel. It already has to travel the ordinary length of the light clock, 186,000 miles. But now the light clock is in motion, it has to travel even farther to catch up with that mirror as it rushes away. So I have these two light beams on two light clocks. They reflect off the mirrors, and they must come back to their point of origin at the same time. But one of them has a lot farther to travel. It has to travel the length of the light clock and then some. And moreover, the speed of light on both light clocks must be the same. So how can it be that the light beam travels the length of the light clock and then some and still manages to make it back in time? The only possibility is the length of the light clock must be shorter.
Definitely. There's no other way. If everybody agrees on the events, then it must be getting... This is an excellent proof. That is a knockout. That's a knockout proof.
The length of the light clock contracts so that the mirror isn't as far away as you might have thought it would be. And since now the light beam doesn't have as far to go, it can make it back in time to greet the other light beam at the same event at the same time. Now again, so far we've only shown that this very strange device with two light clocks set up perpendicular to each other will actually shrink in the direction of its motion. But what about an ordinary device? What about me when I get inside a spaceship and I travel at 99.5% the speed of light? Will I actually shrink?
No, that's impossible because there's multiple people observing you. You can't, right? So some of them are observing you and they travel as fast as you. Some of them are observing you and they're traveling fast relative to you, and some of them half fast. And there's different people observing you at different velocities. So you can't be Heisenberg shrinking or contracting and not contracting. Therefore, it cannot be physically happening to you. It must be an observed phenomenon.
Again, according to the principle of relativity, I must shrink. If I didn't, a person on the spaceship could tell that they were in motion.
Relative to the observer, yes, you shrunk physically. But relative to yourself, you didn't. Nothing happened.
Absolutely, by checking whether the light clock had gotten smaller compared to me. The only way for the laws of physics to be the same on that moving spaceship is for both the light clock and I, the observer, to shrink in the direction of motion. So I shrink. How do I shrink? Is it uniformly? Do I become a small person? Do I get shorter, thinner? Well, it depends on the direction of motion. If I'm sitting up straight and moving to my right, I will get thinner in the direction of motion. On the other hand, if I were moving upwards in the direction of my head, then I would get shorter. That is, objects shrink in the direction of motion. In summary, you've just learned about time dilation, that an observer viewing a reference frame in motion will view the clocks on that reference frame to have slowed, and length contraction, that an observer viewing a moving reference frame will view the lengths in the direction of motion to have contracted. And you might be thinking to yourself, but why? Why do they do that? Why does time slow? Why does space contract? And according to Einstein, the only answer is because of the light postulate and the principle of relativity.
That's not a mechanical explanation. That's not a because. Oh my God.
Einstein's formulation of relativity in terms of these two postulates is sometimes called a principled theory. It is a theory where all the consequences of the theory follow from two principles. And that makes sense given the context that Einstein was in. He had just
a principled theory. It's not a scientific theory.
Discovered some of the basic effects that lead to the theory of quantum mechanics. So he knew that physics was about to be completely revolutionized. And if you're in that situation where you're worried about huge parts of physics getting thrown into the garbage bin, you might try to formulate the whole thing with as few principles as possible. Just the principle of relativity and the light postulate. And that might not feel very satisfying. You might want some kind of force to pull space together or slow time down.
Yeah, exactly. You want you want a scientific theory. This is science. This is not science fiction. We want a scientific theory. We want a mechanical explanation.
Or you might want it to be a fact about the basic geometry of space-time. And it is a philosophical question how you interpret these properties of special relativity. Philosophers sometimes suggest that we should be looking for something more, constructive theories, where the meaning of constructive is not always so clear, but some kind of theory that allows a more elaborate explanation of where the effects of special relativity come from.
Ah, there you go.
Next lectures, we will give one such explanation in terms of the concept of a space-time. And if you think all this is weird or incredibly exciting, that time slows down and length contracts, it's only the beginning. Come back next time when we'll talk about the concept of simultaneity and how it doesn't mean what you might think it does. Thanks, folks. Stay safe. We'll see you next time.
Stay safe. Stay safe. Okay, that was very good. That was very good. So the question is, so the rubber ducky must contract, but not to us observing the bathtub. It must contract relative to a rubber ducky observing. That's all. So a rubber ducky, so we can show length contraction for a rubber ducky. Meaning two rubber duckies, because it's not us, it's rubber duckies. Two rubber duckies will observe length contraction. This is very good. But notice that he already disproved why an interferometer should work. I mean, that is the proof, because of simultaneity, because we all agree let me think. Pretty much. Pretty much this single-handedly explains why the interferometer must fail. Where's the interferometer? This guy. This is an interferometer. So, right? With the ether moving. The ether is moving. So because the ether is moving, right? It's given that they're going, well, they're not, there's no coupling here. So you could say, why does this need to contract? Why wouldn't this keep on pinging at a different rate than this? Why must they have the same rate? So we need to figure this out. This shouldn't happen, actually. They should go out of sync as you're moving. Why should they remain in sync? If we actually have an ether, then this should, I mean, and we're looking at it. Where's the original? This guy. So the rubber ducky does this undergo length contraction? Well, it cannot undergo length contraction relative to us because we are also undergoing length contraction. Everyone is undergoing length contraction. So as this is length contraction is just what an unmoving or the unprimed, I think it's the primed. I don't know which one. So let's say this contraption is moving. This is not so simple. Time slowing down is very simple. But what about length contraction? That's not simple. Length contraction is just me observing a phenomenon and receiving we need to look at simultaneity. How
In the last video, we learned about how for a moving observer, time slows down and lengths contract. Einstein just couldn't make sense of these strange results until he realized the following thing, that there is no fact of the matter about whether two spatially separated events, like the snapping of fingers, happen at the same time. In this video, we're going to learn about the relativity of simultaneity.
that was good. That was good. Like two simultaneous events. That's not simultaneous. That depends.
Hello, folks, and welcome back.
Who is this guy? Very good. Associate professor, philosopher of physics. That's why he had this insight that we're looking for something deeper. Look at that. Wow. Director of the LSE Center. Wow. Look at this. He says space, comma, time, and gravity. He separated space from time. He doesn't say space time. Rumble is in Toronto? Let me compose an email to hello.
What's up, my N-word?
Hey, are you a doctor?
No.
Do you know physics?
Physics is not a branch of any science or of any value. What do you want to know? I'm good at knowing stuff.
Like, do you know, can you explain length contraction?
Length contraction.
Yeah, relativistic Einstein theory of special relativity, length contraction.
Yeah, no, I don't look into Einstein shit because most of it's just garbage.
What garbage?
Most of the stuff from Einstein is garbage. They just made shit up. They're liars.
So you think special relativity is garbage?
Yes.
Mm-hmm.
Obviously, I can't prove it to you, but you can't invent a theory about space when you can't go to space. So
What?
there's no
No.
logic to it.
There's nothing to do with going to space.
Huh?
Special relativity has nothing to do with going to space. I mean, it's good that you're questioning. It's good that you're skeptical.
Mm-hmm.
But special relativity is not about going to space. Special relativity is from 1905. No one went to space in 1905.
So
Yeah.
I just pulled this thing, right?
What?
On the third dynamics of moving bodies, the theory is presented as being based in two postulates. One, laws of physics are invariant to all inertial frames of reference. This is known as principle of relativity. The speed of light in a vacuum is the same for all observers, regardless of motion of light source of the observer. This is known as the principle of light constancy or the principle of light between variance, the first postulate. Okay, it's junk.
Why?
Because the problem is they had no way of measuring the speed of light. It was just a theory.
What? No.
Right?
They measured the speed of light. There's ways to measure the
How?
speed of light. They used I mean, there's videos on YouTube how to do it, of how people did it.
Okay, fine. So the common belief is that the sun was 93 million miles away, and the speed of light was 1 AU, wasn't it?
It doesn't. This doesn't
light
concern the
sun to the
sun.
earth.
This doesn't concern the sun. This is just on Earth, just measuring the speed of light.
Yeah, no, it's crap. Because like, let me tell you something. The speed of light in a vacuum, like we don't measure things in a vacuum. And why would you bother testing things in a vacuum? Because the theory was that the space is vacuum. Based on no evidence.
Look, it's good that you're skeptical,
Mm.
but your skepticism, it's I don't know. I mean, you're right. I never tested the speed of light. So the speed of light, if I test it, it might not be a constant. I'm just going with what I'm being told. So that's not good. I need to look into this. So
But would you say it's more of a marketing thing than based on reality?
marketing?
Well, the government has always been marketing Einstein and right for these theories. And what's a theory? What's the definition of a theory? Right? It's just an idea.
Look again. I appreciate your skepticism and that I know how you feel. That it's difficult to tell. I mean, we're surrounded by so much disinformation that I know how you feel.
No, this is disinformation.
Well, so I don't know because how do you know? How do you know? I don't know. I don't know either way. So
Okay, let me explain to you. In 1905, they had no way of knowing anything. Okay, they
How
had
do you?
no modern technology. They had no way of measuring the speed of light. It was all theory. It's like 16th century googly dosh of the 20th century. So there's no basis for it at all, and this is why physics is dead.
No. Look, you're being assertive, just like they are. So like you need to be skeptical about your position just as much. So you can't just assert they didn't know, they didn't have technology. I don't know what they had. And I don't know if it's even relevant. I honestly don't know. So I need to figure it out based on
Yeah,
very
but you're using all your energy to figure out something that is not worth figuring out. What's the point? We don't know if the stars are moving or fixed. We don't know if we don't know the truth about all this.
well, but for me it's fun to try and solve this puzzle. For me it's like a puzzle that I can't sleep until I crack it. I'm so curious.
Okay, fine. So the problem is, right, I can go outside and I can look at the moon, I can look at the sun, and I can look at these so-called planets,
Mm-hmm.
right?
Mm-hmm.
And it's obvious they're just lights in the sky. They're not of it. They're not of any, they're not of any, what's the word, body. They're not big masses of metal and wood and rock. They're just lights, right? That's what I
Okay.
can ascertain. And
Okay.
these objects are so close to me, I can make out features of them.
Mm-hmm.
I can physically see how close the stars are. They're not billions of light years away. Right?
What's
But you can see if they were billions of
okay,
if
but
they were
this
billions of light years
it's a
away.
different topic. I understand that you're skeptical about astronomy. That's fine. That's a different. That's also something that I'm not curious about. That I'm not curious about. That seems to me like a very simple explanation is that the sun is at the center of the solar system and so on. Like that doesn't bother me. What does bother me is special relativity, general relativity, and quantum mechanics. That's it. I need to figure these out. Like right now, I need to figure out special relativity. Like, is it true or is it false?
So, okay, give an example, right? Now, you understand Einstein was Jewish, right?
I don't know. I don't. Why is that even important? Who cares?
Well, okay, now fine. So, do you understand that, like, our education system and our universities and our governments have been hijacked predominantly by Jewish people?
I don't care. I don't care about anything.
I'll get to that. Okay. Well, you've got to understand politics.
I don't care. I only care right now about special relativity. Is it correct or not? Can I figure it out with the very
Okay, fine.
limited
Now, I've got a better idea for you. Instead of doubling down on these theories, why don't you just create your own theory and just make it up like they did? Fuck it. Why are you bothering?
That's what I'm trying to do. I have my own theory,
There you
the
go.
ether theory, but I'm rethinking. I'm rethinking. Like, am I correct or am I wrong? That's exactly where I'm at. Like, was Einstein right or was Einstein wrong? Am I correct? Am I wrong? That's exactly where I'm at. And that's why I need help to figure out length contraction. Time dilation is easy. Length contraction is now I'm confused by length contraction. So like I believe.
Yeah.
What? What did you
I'm,
say?
I'm just saying, like, but people are racking their heads and trying to memorize all these theories,
I don't care.
but
I
they're
don't.
not.
I
But it's
don't.
keeping you distracted from finding out the reality.
No, I don't care about people. I care about reality. I don't want to be distracted. I want to figure out reality. I want to understand. So I understand time dilation. Time dilation. So I have come up with a theory of ether. So according to my ether, immediately I get the constant speed of light and I get time dilation. And now I'm up to length contraction. So is there length contraction? I'm wondering. Time dilation, I agree with Einstein. The constant speed of light, I agree with Einstein. What about
Yeah, but
length?
he the problem is he came up with these theories when they had no modern technology.
So,
He was actually going against the grain, just making shit up.
so,
And during that period, people were doing great things like improving engines, making aircraft, and discovering all these new chemicals and drugs and things like that. And things were going really well. But we have to listen to Einstein, who was trying to make up theories about light in a vacuum. It's stupid.
I'm not
Like
listening.
there's no purpose to it.
Wait, I'm not listening to Einstein. I'm looking. I'm just, I. It happens to be that I agree with him. I don't care what he said. It just happens to be correct. What he said, I happen to agree with. My ether theory agrees with Einstein's idea that the postulate that the speed of light is a constant and that we get time dilation. So he happens to be correct about these two things. Now, the next question is length contraction. Was he right about length contraction? That's my.
Okay, fine. I just found an abstract here. Critics often find it difficult to accept concepts such as time dilation and length contraction, which occur at speeds approaching the speed of light.
What?
So,
What was the first thing you said?
what's the point?
What?
What's the point? Why are you bothering with this shit?
I'm
Go
curious.
down and
I'm
you
curious.
could just go at. Why don't you go out there and create something, or I don't know,
I did.
do something amazing?
That's what I'm working on. I'm writing a paper. You're catching me exactly as I'm writing a paper about my
Yeah,
ether.
well,
That's what I'm trying to do. So as I'm trying to sit and
Einstein was an idiot.
I don't care. I don't care if he was. I don't care. It's not important. I care about the universe. Is length contraction real or not?
Well, okay, fine. So length contraction refers to what? The expansion and contraction of the so-called universe. Is that what you're saying?
The what? Wait, what did you say?
What's it referring to?
Length contraction is that if you observe something moving, then you measure it shorter. The more it's moving relative to you, the more you measure it to get shorter in the direction of the motion relative to you.
Oh my god! Yeah, no, please don't. I'm not even going to entertain all that because it's so ridiculous and pointless.
Okay, but you have to disprove it. You can't just reject something with no like
It's a theory.
Yeah, it's a theory.
A theory means we can't prove it. We don't know what it is. I can't justify it, but I would say it anyway, and people will believe it. Okay, you can't physically go to space. There's no satellites. There's no spacecraft. There's no probes in Uranus or
That's
whatever the fuck it's
irrelevant.
in. It's all bullshit.
It's irrelevant. And you're being as assertive as they are. So that's no good. You need to be skeptical. I'm not assertive. I'm always skeptical.
Mm-hmm.
You don't know. You need to keep an open mind. What's the point of just asserting? You can assert anything you want. You're going to live a life of lies if you live in your assertions. What's the point
That's
of
actually a good point. I am asserting a lot, but also, but if you're not asserting, then also you're being submissive and you're under a paradigm of the government. So how's that any fucking good?
No,
look at where that's got us.
I
Have a
agree.
look where submissiveness has got us.
I agree.
It got us into mass extinction, mass wars, mass poisonings,
I
mass immigration,
agree.
mass corruption.
I agree. I
mass
agree.
genocide.
I agree. I
So we
agree.
should be asserting more and telling the government to fuck off and develop our own systems of government.
But then
not this stupid science-based system that we're living on. It's bullshit.
No. You are reacting to the assertions of the government with your assertions. You shouldn't do that. You should react with skepticism. Like you don't want to
No, reaction means that you've already lost the argument.
Listen, they're forcing
That's
you.
the point.
Listen. You're complaining that they're spreading lies, and in reaction, you're spreading your lies. So you shouldn't do that.
I'm not lying.
You're asserting. That's lying. That's just a nice word for lying. You should not assert. Asserting is lying. That's what they're doing. You hate them for lying, for spreading lies. So in return, you're spreading your own lies. So you're the same as them. It's just lies and lies. Everybody's living in infinite lies. Instead, just be skeptical. That's it. And if you can if you can prove them wrong, that's fantastic. That's what I'm trying to do. I'm trying to prove Einstein, I don't know if wrong, but superfluous, or I'm trying to reduce.
Yeah, but the thing is, but the thing is, he gets propped up by the establishment, right?
I don't care.
No one buys it.
Look, it might be true. I don't know. Again, you're asserting. I don't know. I don't care. I feel I can reduce him to his proper size. I agree with you that something is wrong with Einstein. Something is wrong. I feel something is wrong. I think but it doesn't matter. It's either I can prove it or not. And I'm working on a proof. So right now I need to understand what he said about length contraction, about what he said about the constancy of the speed of light. I understand. I got him figured out. And I have a paper that proves him incorrect. He basically. So the speed of light I have figured out. Time dilation.
Okay. How did you figure out the speed of light? This is.
That's easy. The speed of light is once you assume ether, then you get a constant speed of light. So that's easy. So the speed of light comes directly out of ether. So that's easy. Once the speed of light is a constant, so time dilation, once you assume ether, you get time dilation as well. So you get the speed of light as a constant. Why do you keep going all the time? Like, what do you?
Okay, I'll stop doing it.
No, I'm
It's just a
asking.
habit I got.
Why do you do that? Like, are you being skeptical?
I don't
Or are
know
you
why.
being like? Why do you do that?
Well, okay, no, I'm just listening, but I'm not. I'm just sort of agreeing with you.
Hmm.
Okay, that's what I'll stop doing it.
No, I'm just making sure that you're not doing it like you're mocking me. That's all. Like if you're not getting it, like I don't want you to get upset. Yeah, I'm just asking. Like you can make any noise you want if that's what you're used to. It's fine. I always make
All right,
noises
fine.
too.
Yeah, go for it.
Anyway, look. So speed of light constant comes directly out of my ether theory, so that's fine. And the time dilation comes out of my ether theory, so that's fine. The next question is length contraction. Look, there was, the Michelson-Morley experiment?
Is the Michelson Morley one with the balls and the fucking
No, that's a
the movement?
Cavendish. That's Cavendish, I think.
Yeah, the Cavendish one is by far the stupidest, most pointless, useless experiment in the history
No,
of mankind. It is
no.
absolutely ridiculous.
What you say that about everything? Why do you say that about everything?
But it doesn't prove anything. What, you push a ball, then it keeps moving for a couple of minutes and it stops?
Oh, I don't know. Never mind. Look, let's get back to length contraction. So, look, there was the experiment of Michelson and Morley's when they discovered that there is no ether. They couldn't detect the motion of the ether. Are you familiar with the ether?
I have heard of these theories, but
Hmm.
it is theories, yeah.
Anyway, let me make you my friend because you're a good person. You're nice to talk to.
Ah.
I enjoy.
Are you a globetrotter?
I'm a globe-tard. I believe that the planet Earth is a globe. Yeah, I'm a globe-tard.
It's flat. It's 100% flat.
Look.
Because look.
No.
The problem. Look, let me tell you something. They developed all these theories about the spinning ball, and they tried to get out there and tried to make it work and tried to prove it. And eventually, they realized they couldn't really prove it, so they just developed experiments that looked impressive, that could be replicated, that could prove.
I understand.
They never
Look,
did it.
I understand. Look, I told you. I understand and I appreciate your skepticism. But you're being but you're assertive. You're asserting. You're asserting. I don't assert. I think.
You're going to assert falsehoods.
What?
Because it's the truth.
No,
That's what the facts are. The earth is
you don't
flat.
know. You don't know. You should always put a question mark after everything.
No, we're
Yes,
beyond that.
you
We
should.
know it's flat now. It's
You
over.
don't
We don't need
know.
to go back to the 16th century again. I don't want to.
You don't know. You don't know. You don't know. I don't know. I'm a globetard, but I'm still skeptical. Like when you say the Earth is flat, I say I appreciate your skepticism. I don't say you're wrong. I would never say you're wrong. I would just
But
say
you can look at all these theories,
I
and they're
agree.
just theories.
I
They literally
agree.
call it a theory.
I agree. I agree.
Okay, good.
I am the ultimate skeptic. I agree that we should be skeptical. I agree that it's just a theory and we should be open-minded. It could be wrong. I agree. That is the essence of science. I agree. Yeah. But then but then you start asserting they're lying, it's a conspiracy. That's an assertion. You don't know that. You could say maybe there is a conspiracy, maybe they're lying, maybe it's all for money, maybe it's government. And sure, I would agree that, that's a good theory. I'm sure, like a professor in university who makes his living from physics, he doesn't want to find out that his physics is completely a government conspiracy. So he could be part of a government conspiracy. It could, it would make sense. I mean, but it's, to me, it's unlikely. I mean, it's just unlikely that there is a government conspiracy. There is, like I agree that they're very close-minded, that the academia is an echo chamber and there is problems with academia. Yeah, but when you debate them, you see that they know their stuff inside and out. I mean, they run circles around us. So if you want to bring them down, look. So my father said, don't go to war unless you know you're going to win. So if you want to bring them down, you better be prepared. So, so that's what I'm doing. I'd love to bring them down. I'd like to bring them down at least a notch, if not completely dismantle. Like I hate them, but that's fine. But to bring them down, you need high, like big caliber guns. So that's what I'm working on. So just sitting at home and asserting that they are lying, that's not going to bring them down. That's probably going to help them, if anything. Because they're, anyway, that's my opinion. Anyway, I'm gonna get back to studying my relativity.
I'm going to invent a theory of special longer objectivity.
You need to just study. I would say just study physics. Try to understand it. That's what I
It's a
did.
waste of time.
What? No. Look, you want to bring them
Something
down.
that's based on lies.
Look,
It doesn't make any sense.
you want to, okay, you got to prove it. You can't just assert it. You have to be able to prove it. So in order to prove it, you have to study it. You have to study it and find the weakness in their theories, in their construct, in their conspiracy. You have to find the weakness. You have to find the weak spot and attack exactly there. Like just sitting at home and asserting that they are poop, that's not going to help anyone. That's a waste of time. Talk about a waste of time.
No, but the thing is, look, if you're waiting to react or to submit, no, it's not going to work. You have to be constantly asserting and attacking these
Skeptical.
people because they're
No,
criminals.
skeptical.
They're not.
You don't know
You
that.
keep thinking that these people are like us.
You
are morons, and they're ridiculous, and that they're dumb. Einstein was an idiot.
I wouldn't say
Right?
that.
It was all fake. And, like, there were better people of the period inventing better things and technological, and they couldn't handle it. Like all these European Jews felt so stupid, right? Because all this technology is occurring all around them, predominantly from Germany, right? And they were not. They just didn't get it. And the Jews realized, hang on, we're really stupid.
Why do
they
you
got really
care?
angry.
Why do you care?
The
Why do
Jews
you?
got really angry at Germany, and they declared war on them based on jealousy.
No, that's
Then they
nonsense.
stole their technology and ran to America.
That's nonsense. What are you talking about?
That's what happened.
No, that's not. That's
World War II was based on jealousy and ignorance.
that's nonsense. That's nonsense. World War II, where you had a guy with a mustache.
No.
Yeah. You had a guy
It
with
was
a
it was the Jews who were subverting society and trying to make people look stupid and dumb all the time, right?
look.
And people were fed up with it. Like, these people are idiots. These Jews are dumb.
Look. I don't.
So they basically just
Look. I
they all
don't.
sat around and said, "Okay, we want to kill all the Germans." And they said, "Well, why do you want to kill the Germans?" Because they're smart. Oh, okay, fine.
What?
They all sat around and declared war on Germany in 1933, and the Germans said, "People are
No.
idiots."
That's not what happened.
Yep. Yes, it did.
No, it's not what happened.
Yes, they had a conference in Holland or Netherlands or somewhere like that, and they said, "What are we going to do about these Germans?" They said, "We're going to kill them. We'll declare war on them." So they declared war, and they started trade embargoes and all
No.
this shit. And then they sat around and they corrupted
No,
the whole world.
that's
and
not.
They convinced it, and
You're
the Jews were working inside Germany, blowing everything up and
What
killing
are you
people.
talking about? What are you? That's such.
That's how World War II started.
What are you talking about? You have no evidence for any of this. It's not what happened.
The Jews were working inside Poland and doing raids and communistic raids and Antifa type raids on Germany and murdering ethnic German people within Poland and East Prussia.
No.
They instigated World War II. But Hitler took the bait. He should have. The problem was he couldn't send troops to protect the native-speaking Germans within Polish territory. That would have been a declaration of war, and the Jews knew that, right? They said, "Well, so that they said we'll just start killing all the native Germans." And what I think what Hitler could have done is said, "Let's get out of there," because Hitler wanted to create a corridor of land and to protect the German-speaking people within Poland.
Look,
but they wouldn't allow it. The Jews wouldn't allow it.
Look, come on. This is to me. This has look. I'll tell you the truth. I don't know enough of exactly what happened, but from what I gather, that is not what happened. You
Yes,
had
it is.
well that I heard.
I'll show you.
I heard you. I heard what you said. That's not, that's not what I told you. I don't know. I barely know. I wasn't there, and I don't know. And as far as I know, Hitler was the instigator of World War II,
No,
and
incorrect. It was the Jews.
I just don't see it. I don't see it.
Because Germany had no interest, nor would they gain anything by going to war. And that's why Hitler signed a peace deal with Stalin.
Okay, look, I don't know. I wasn't there. I don't know. Anyway, getting back.
That's all right.
Getting back to Einstein. So
Fuck Einstein.
I don't care about Einstein. All I care about is his special theory of relativity. Theory of special relativity. I need to figure it out. I need to see if it works within my ether framework. So let me get back to my research. I'll talk to you later, man.
I have a good one, bro. Look, I'm not the right person to speak to. As I said, as you know, I'm very skeptical. I'm a historian, and I know that all this is not good. So yeah.
Yeah. Anyway, come back. We'll talk again whenever you want to talk.
All right, see you around, slave.
All right, see you around, man. Bye.
Do you go to that other server by Sea Lion?
Yeah, the Globe Tards. Yeah, I spend most of my time there.
Yeah, the Globe Gangster Tards. Yeah, I've been banned there so many times now. It's ridiculous.
Yeah, I was like they silenced me one day. Yeah.
Hey. Oh.
Yeah. Anyway,
The thing is,
what?
the problem is you start questioning the narrative and they can't handle it.
Yeah. Yeah, they hate me. They hate me because of my ether. So they don't just hate you for
Yeah, work
being.
on that. Yeah, there's been a lot of research done on the East in the past couple of 100 years, so there's a lot of stuff out there.
Well, they hate it.
Stick with it
They hate my ether and they hate me and they're
because
very.
it goes against everything else they've been taught.
Yeah. Yeah. They're very mean to me. They're very condescending. They're always very um they're always mocking me and hurting my feelings.
Yeah, I don't do that to me.
They're always mean to me. Yeah, they're a bunch of meanies. They're a bunch of mean characters. They're mostly
Yeah, they're delusional homosexuals, most of them.
yeah, I was about to say that. They're mostly gay. Most of them are gay, yeah. I think
Yeah,
all
and remember, the gay people have been told, you're smart, you're right, you're doing the good thing, go get married, adopt children. Like, these people are sick. Yeah, people are sick, man.
yeah.
There's something wrong with it.
Yeah. Yeah, I agree, of course. Anyway, it is what it is. Well, I'm not gonna.
See you around. Have a good one, bro.
Yeah, I'll see you around, man. All right. What else we got? What else we got? So we were looking at this guy. Interesting guy. So, I was sending him an email. So, hi, I have a small channel. Your channel. Copy clean link. Here is my channel. I have a small channel about physics. I would love I am currently working on an ether model that is conformal to SRGR and quantum field theory. Please let me know if you're interested, if you are interested. La la la, I would like to interview you. Hi. His name is Roberts W. something. Doctor, associate professor. So he's a professor. Hi, Professor Brian. Professor Roberts. Hi, Professor Roberts. I have a small channel about physics. Channel that is lately mainly about physics. La la la. That's it. J1B. What's so funny? Why are you laughing? All right.
I'm Brian Roberts. Let's start with a little warm-up exercise. You're walking to the park from home, and your house is about a mile away from the entrance to the park. Your friend is walking to the park as well, but she lives...
Wow, she's hot. Jesus. That's a hot chick.
10 miles away from the park. You both walk at exactly the same speed, but you arrive at the park's entrance at the same time. How is that possible? Your friend must have started out earlier. If two bodies travel at the same speed and arrive at the same time, but one had farther to go, that one must have started earlier. This fact, together with the light postulate, is what gives rise to the relativity of simultaneity. It's one of the most important facts about special relativity.
Amazing. He actually builds things up philosophically. He teaches it like... That's why his channel's name is Soul Physics.
To understand it, we have to first say what we mean by simultaneity. For thousands of years, it just seemed obvious. Two things are simultaneous if they happen at the same time. What else is there to say? I'm simultaneously intrigued and confused. What does it mean for two spatially distant events to be simultaneous? Well, Einstein imagined it like this. Okay, we're going to need two events. Let's take a first kiss in Paris and a first kiss in London. Suppose that a light bulb flashes next to each event the moment that the event occurs. And let's imagine that there's a person placed halfway between the two events. Where's halfway between Paris and London? I think somewhere in the English Channel. Maybe it's a person on a raft. We'll say that what it means for the events to occur simultaneously is that...
Jesus Christ. On a raft on the channel. I don't think... Can you survive?
The person placed halfway between them receives those light beams at the very same time. Makes sense? The two bulbs flashed simultaneously.
As soon as you say light beams, you're gonna confuse yourself. Just that Maxwell said it's waves, so just use waves and you'll be better off. Trust me. I'm a scientist.
Simultaneously, a person halfway between ought to receive the light beams at the same time. Now here's where it gets strange. Suppose these two pairs of lovers are in motion, not at rest. Let's say they're on a giant platform which stretches from London to Paris, and the platform is moving at very close to the speed of light. It's another thought experiment, but stick with me. If the platform is moving from London towards Paris, then the observer in the middle is rushing away from the London light beam and rushing towards the Paris light beam. That means that the London light beam has farther to go in order to reach the observer, and the Paris light beam has less distance to go in order to reach the observer. Now, the light postulate says that both these light beams must be traveling at the same speed, and they both arrive at their destination at the same event. Do you remember our warm-up from the beginning? Two bodies traveling the same speed that arrive at their destination at the same time, but one has farther to go. That one must have started out earlier. So when that platform is in motion, I can no longer say that the two events, that first kiss in Paris and the first kiss in London, happen at the same time. That first kiss in London must have happened earlier than the first kiss in Paris, so that the light beams could set out and arrive at the person in the middle of the platform at the same event. But why is London different than Paris? Why does London happen first? It just depends on than the first kiss in Paris, so that the light beams could set out and arrive at the person in the middle of the platform at the same event. Why is London different than Paris? Why does London happen first? It just depends on the direction of motion. Suppose this giant platform were moving inertially in the opposite direction, from Paris towards London. Now an observer observing this platform whiz by will say that the Paris kiss happened.
I mean, obviously, this is yelling that this is happening inside a fluid. This is obviously fluid dynamics. This is just waves in a fluid. It's like, how could people not get that this is waves in a fluid?
And before the London one did. Wait a minute. So do these first kisses happen at the same time or not? Who fell in love first? Well, that depends on who you ask. There is no fact of the matter about whether these two events occurred simultaneously. One observer will judge that they did happen, and the other observer will judge that they did not happen simultaneously. Let that sink in for a moment. There is no matter of fact about whether two spatially separated events occur simultaneously. But what about a band in which we're all placed in different parts of the room and we all begin at the same time, simultaneously? That too is not a matter of fact. An observer whizzing by at close to the speed of light would say those band members are out of sync. What about two babies in different hospitals with the same birthday and birth time? That's not a matter of fact either. Whether or not they're really born at the same time depends on which observer you ask.
I've never heard anyone explain SR so clearly, so crisply. This is only someone who does philosophy. This is philosophy. He's a philosopher of physics. That is powerful. That is powerful. So the name of the channel is Space, Time, and Einstein by Brian W. Roberts. Wow. How many videos? Only 11 videos. That is so few. Oh my God. And they're probably all very short. 4 years ago, 3 years ago, and that's it. So it's a 9-part essay. So here, this is 4 years ago. Let me see the length of the hair. It's basically the same length. So what date was it? The date. What date? The hair is almost identical. And this is the same jacket. This is a different jacket. It's very thin. Big eyes. Jesus. He looks Italian. What's his last name? Roberts. No, that's British. That is British. What is the LSC ACUK/Robert? What is that? I'm a philosopher of physics, lost artist, and associate professor LSC, where I direct the Center for Philosophy of Natural Social Sciences, CPNSSS, from 1922. I also taught in the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge. I work on foundational issues in quantum theory, space-time, one word, and gravitation, thermodynamics, gauge physics, and other things that fill one with wonder about the world. I am also an advocate, there you go, in improving LGBT rights at the LSC, about which one can learn a lot here. I animated and recorded a series of YouTube videos introducing Einstein theories. Very good. Courses, Einstein for Everyone, Physics and the City, Philosophy of Science, Genes, Brain, Society, The Big Questions. He wrote a book. Reversing the Arrow of Time. I wrote a book about the Arrow of Time. It was published 22 by Cambridge. This project completely changed how I look at academic book writers, not to mention my bookshelf. You poor things, what a remarkable journey you all embarked on. Buenos Aires. Why do we become older but not younger? Space-time symmetries, origin of antimatter. Good news about killing people. Time reversal. Some curious examples, mathematical representation. Weak interaction, curious little arrow of time. Noodling, a Wurlitzer, preprint abstract. Gauge argument, neither reason. Leibniz equivalence. Where's the link? Why doesn't the link come up? The abstract doesn't have a link. The preprint has. Wow, this guy is keeping busy. Dissertation. Time symmetry and structure study in the foundations of quantum theory. Supervised. Podcast. How to win an argument. Is science morally neutral? Humans, not robots, are the real reason artificial intelligence is scary. Oh, London School of Economics and Political Science. That's LSE. E stands for economics. This is X. Let me sign into Googly Goog. Let's try this again.
We'll start with an experiment. I mean, surely if space doesn't exist, then I couldn't use it for anything. So I'm going to try and show you a sense in which I can use space for something. This might be a trick, but I want you to think carefully about it. So I have here a 10-pound note. Is it an ordinary 10-pound note? You can keep it if you give me 5 stars at the end of this. What I'm going to try and do for you now you have to watch very closely, is I'm going to kind of scrunch together space as best I can. I want space to sort of bunch up and allow me to sort of set something right on top of the space. How am I going to do that? Well, I'll just sort of go like this. I'll sort of use lots of different sides of the space and move it around into one place. I know you think I'm going crazy right now. But now if you're very careful, you might be able to just use space. Hang. And it's all sides of it, isn't it? Okay. So maybe you'll change your mind about what space exists.
Wow. Good job. hmm Divest from genocide. Solidarity with Palestine. The Palestinian people. The people of the Palestine. Alright, whatever. Okay, let's get back to reality.
Simultaneity is one of those concepts that we assumed for thousands of years must be absolute, a fact about the nature of the universe. And it wasn't until Einstein in 1905 that we
Wow, he says Einstein.
realized that assumption was false. Okay, but maybe it's not so weird, like lightning and thunder. Usually I see the flash of lightning and then I hear the thunder. Maybe relativity of simultaneity is like that. No, it's not like that. The lightning bolt and the thunder crash really do happen at the same time. It's just that light travels a lot faster than sound does through air. And so it seems like the light happened earlier and the thunder happened later. This is just one thing moving slower than the other. But the relativity of simultaneity is deeper than that. It's not just that it might seem two events are not simultaneous. Only once we choose an inertial reference frame can we say that two events are simultaneous or not. Now, the relativity of simultaneity is not just weird, it's also useful. It helps us avoid certain paradoxes that might have occurred if we had just left it at length contraction and time dilation. This will help you see part of why Einstein thought the relativity of simultaneity was so important to understanding special relativity. Here's an example of how the relativity of simultaneity really saves the day. Suppose that for my fancy car, I designed an absolutely perfect garage, made to fit the car exactly. Down to the millimeter, my garage is the same size as my car. And suppose I have a car door on each side of my garage. Maybe I don't like to back up very much. I am so sorry about your bushes, ma'am. Now I decide to drive my car really fast into my garage at, say, 86.6% the speed of light. And imagine I close both doors the moment the car is perfectly inside the garage and then lift them up again so that the car can continue to pass through. Now, if my friend is standing next to the garage watching all this happen, Brian, you park like a maniac. My friend will see a car moving really fast, and so it will contract in the direction of motion. Remember length contraction. All bodies contract in the direction of motion. So according to my friend, my car will shrink. How much? It turns out to half its original length. So it's actually just a little short car. Ah, look at your short little car. The car has plenty of room in the garage. The doors close simultaneously, then open again, and the car continues passing through. But now compare that to my perspective driving the car. Relative to me, I'm at rest in the car, and the whole world is whizzing by at 86.6% the speed of light, including the garage. And now that garage, which I had designed to be just the same size as my car, has now contracted in the direction of its motion. It's only half the length that I designed it for. And I couldn't possibly fit the car in this garage. It's too small. But remember the experiment. The doors slam shut the moment the car is completely inside the garage, but the car is never completely inside the garage. If I slam the doors shut while the car is inside, it's just gonna smash my car. How can these perspectives both be possible? Will the doors smash my car or not? Relativity of simultaneity saves the day. The closing doors only seems like a problem if we assume that both doors close at the same time in every reference frame. That is, that they close simultaneously. But we just learned that that's not true. They might close simultaneously for my friend standing next to the garage. From my reference frame, sitting in my car, I see this garage hurtling towards me. And just like the lovers in Paris and London, the events don't happen at the same time. The trailing event of the closing door farthest away from me happens first. The door closes and opens again. Meanwhile, I pass through the garage and make it past the other door when it finally closes and then opens again. The closing of the doors does not happen simultaneously in the driver's reference frame, and so my car doesn't get smashed after all. Thanks, folks. I'll see you next time, but maybe not simultaneously.
Unbelievable. Very nice. Very nice dissertation. Very nice. Very nice. You very, very good. You very good, Anakin. Very good. You know what? Let me... Okay. Let's see.
Did you ever wonder whether time could slow down? Whether space could change depending on your frame of reference? Did you ever wonder whether the universe has a beginning or whether time travel is possible? Well, there's a sense in which the answer to each of these questions is yes. These are just a few of the lessons of Einstein's theories of space and time, special and general relativity. What are Einstein's theories about? Why do we think they're true? What are their philosophical implications? Space, time, and Einstein was created to make answers to those questions available to everyone at a level accessible to everyone. We even follow a book by John D. Norton called Einstein for Everyone. You can read along as you go. We'll start with special relativity and learn about things like time dilation, length contraction, and the relativity of simultaneity. We'll also look at some philosophical questions like whether the passage of time is real. We'll then turn to understanding general relativity, Einstein's theory of space, time, and gravity, and his proposal that the force of gravity is just an illusion, and that it's rather curved space-time, together with a principle of motion called the geodesic principle that explains gravitating behavior. In that section, we'll look at time travel, black holes, and the Big Bang, as well as other philosophical questions about the nature of the geometry of space. The course will be given by me, Brian Roberts. I'm a philosopher of physics and associate professor, director of the Center for Philosophy of Natural and Social Sciences at the LSE. Subscribe if you want to follow the course, and thanks for watching Space, Time, and Einstein.
Space time.
Hello, folks, and welcome to Space, Time, and Einstein. I'm Brian Roberts. We're about to go on a journey into some of the most shocking developments in all of human thinking, Einstein's theories of space and time. Some of the most curious results about this theory have to do with the nature of motion, especially motion that's happening at breakneck speeds near the speed of light. So to prepare you, we're going to start with a little bit of background information about inertial motion and reference frames. With these simple ideas in mind, you'll be ready to dive into Einstein's theories of space and time. Hi, folks. Our first piece of background information is about two different kinds of motion, inertial motion and accelerated motion. Motion is called inertial if it is constant speed in a straight line. That's constant speed in a straight line. If you are changing your speed by speeding up, it's not inertial. If you're slowing down, it's not inertial. If you're changing direction, it's not inertial. For us, accelerated motion will mean any motion which is not inertial. This is not just like in English.
What if there is a gravitational field?
We say acceleration means speeding up. For us, acceleration means speeding up or slowing down or going around a curve or basically doing anything which isn't just constant speed in a straight line. If it's a person, an observer who's moving around space and time, I will sometimes call them an inertial observer. And if it's an accelerated person moving through space and time, we'll call them an accelerated observer. Now, how do we measure motion in space and time? For that, we need a reference frame. A reference frame is a system of measuring lengths and times. And if you know about length and you know about time, then you know about velocity. You remember how that works? All I have to do is check how far I went and how long it took. The distance per unit time, that's the velocity. What about when my things are spread throughout space and time and they're moving around? How do I measure that? Well, I'll need a whole lot of rulers and I'll need a whole lot of clocks. I begin by synchronizing a bunch of clocks and placing them at different positions in space. For example, at the beginning of a train track and at the end. Now I set my train in motion from one place to the other. I see when it started on the first clock and when it ended on the second clock. And I know how far it is in between. And from this information, I can calculate how fast the train traveled on average to go from one point to the next. A reference frame is a system of measuring devices just like that. It's a system of rulers and a system of clocks spread throughout space and time so that I can measure motion whenever I feel like it. Now, if I really wanted to measure any arbitrary motion, I would need rulers and clocks spread throughout space and time. And I can't exactly do that. It would break the bank, damage university budgets. That's okay. To be a reference frame doesn't require that I actually place rulers and clocks everywhere in space and time. It just has to be the case that I could in principle. This is sometimes called an idealization. Now that we know how to measure motion, here are two different concepts of motion which are crucial for understanding special relativity. The first one is called relative motion. Relative motion means motion with respect to another thing. So when I'm driving a car, I'm moving relative to the trees alongside the road. But curiously, when I look out the window and somebody's driving in the lane right next to me at the very same speed, that car almost looks like it's just hovering next to me, as if we're both at rest and the whole world is zipping by us. If I'm moving at 70 miles per hour and the car is also moving at 70 miles per hour in a straight line in the same direction, then we are not in relative motion. We're at relative rest. Notice this crucial thing. Relative motion requires two objects. One thing moves with respect to another. The second concept of motion is one due to Newton. It's called absolute motion. Now here it is in Newton's own words. Newton said, absolute motion is the translation of a body from one absolute place to another, and relative motion the translation from one relative place to another. For Newton, there was a concept of an absolute place, not where you are relative to me, but where you are, period. Absolutely. Newton thought about space as a substantial thing that exists in reality. So we could say in particular whether something is in motion or not. Absolute motion with respect to space itself. Einstein's theory ejects this notion completely. There will be no absolute motion in special relativity, only relative motion. So some things you should have in your head so far. Inertial motion is motion at constant speed in the same direction. And accelerated motion is just non-inertial motion. A reference frame being a system of rulers and clocks for measuring lengths, times, and velocities, and you learn the difference between relative and absolute motion. Hello, folks. This is the first lecture on special relativity, and I'm going to teach you the entire theory of special relativity in just a few short minutes. As it turns out, there's only two principles in special relativity: the principle of relativity and the light postulate. If you know those two things, everything else is just a detail. The principle of relativity says that the laws of physics are the same in every inertial frame of reference. How can there be two different inertial frames of reference? Well, one could be on a train. I've set up a bunch of rulers and clocks on my train, and I say these rulers seem to be at rest on my train. This allows me to look out the window and say those trees are passing me by. The trees are
No. So Lenny Susskind says the principle of relativity is the principle of juggling. You can juggle on a train, or you can juggle or off a train. The laws of juggling are maintained. That's the principle of relativity. All the laws of physics, which exist within the laws of juggling. Your juggling doesn't care if you're juggling inside a moving train or if the train is at rest.
are in motion with respect to the train. They're in motion with respect to my train's reference frame. Similarly, someone on the side of the tracks will have a reference frame set up at rest with respect to the tracks. And they'll say about me on the train that I'm the one that's moving. Now, the principle of relativity says that as long as we're each moving with constant speed in a straight line, we will have the same laws of physics. You might have heard of this one. It's called Newton's first law. Every body continues in its state of rest or in uniform motion in a right straight line unless it is compelled to change that state by forces impressed upon it. Bodies in motion will stay in motion. Bodies at rest will stay at rest unless acted upon by an outside force. Newton's first law is true in every inertial reference frame. Let me try to give you an intuition for what that means. You held a cup of coffee in your classroom before, and you were at rest. And the coffee just sat there in the cup until you decided to have a drink. But compare that to holding a coffee in your car when your friend driving decides to slam on the brakes. What happens?
Who holds a cup of coffee like that? No one does that. You have a handle. Jesus.
Your coffee spills all over you. I just bought these pants. I can't believe it. The difference between those two motions is that one was inertial and the other one was accelerated. When motion's inertial, you almost...
That happened to me so many times. When you buy coffee, usually at Starbucks it wouldn't happen, but at McDonald's it happened multiple times. They don't close the cap and it spills all over.
Can't tell that you're moving at all. It's sort of like being on a plane. When you wake up, you start to hug your pillow only to realize you're not home at all. And that your pillow is the person's arm next to you. I'm very sorry about that, sir. Am I the only one that this happens to? As long as the plane is moving in a straight line...
You're the only person that ever happened to, yes. One of my flights, there was a beautiful Chinese chick next to me. Jesus.
Constant speed, it is very much like your bedroom. Coffee doesn't spill on you, it feels like you're at rest. Newton's law is really different from what they used to believe in, for example, ancient Greece. That if something was in motion, it would slow down until it got to its natural state of rest. True, absolute rest. That law is saying a body in motion will change. It will come to a rest. A body at rest will stay the same. These are two different reference frames and two different laws. That means it's incompatible with the principle of relativity. The principle of relativity is sort of like a meta law. It's telling you about how the laws of physics must be. And it says in particular, whatever they are, they must be the same in every inertial frame of reference. Now, there are a couple of interesting implications of this principle alone. One of them is absolute motion cannot occur. If the principle of relativity is true, which reference frame would it apply to? This one or that? Well, the laws of physics have to be the same in every reference frame. So we can't identify one as being absolute motion. Another consequence is this. The laws of physics tell us what kinds of experiments are possible. If the laws of physics are the same in every reference frame, that means that experiments will run in the same way in every reference frame. Galileo put it in this charming way. He said, imagine you had a laboratory on a boat, and that the boat was moving with very constant speed in a very straight line. I have all kinds of experiments I can set up. I've got an inclined plane. I've got a large hadron collider experiment that passes through a small space. I've got some butterflies flying out of a bottle. No butterflies were heard in the making of this video. Oh, I love butterflies. Whatever experiments you like, I set them on a boat, and I compare them to the very same experiment set
That's the juggling.
up on Earth. If the motion is truly inertial, the results of all those experiments will be the same. If the ball rolls down the inclined plane on the boat, it will do so on Earth.
Oh, this is Galileo's. Wait, did he say it's Galileo's?
With the principle of relativity. The principle of relativity is sort of like a meta law. It's telling you about how the laws of physics must be. And it says in particular, whatever they are, they must be the same in every inertial frame of reference. Now, there are a couple of interesting implications of this principle alone. One of them is absolute motion cannot occur. If the principle of relativity is true, which reference frame would it apply to? This one or that? Well, the laws of physics have to be the same in every reference frame. So we can't identify one as being absolute motion. Another consequence is this. The laws of physics tell us what kinds of experiments are possible. If the laws of physics are the same in every reference frame, that means that experiments will run in the same way in every reference frame. Galileo put it in this charming way. He said, imagine you had a laboratory on a boat, and that the boat was moving with very constant speed in a very straight line. I have all kinds of experiments I can set up. I've got an inclined plane. I've got a large hadron collider experiment that passes through a small space. I've got some butterflies flying out of a bottle. No butterflies were heard in the making of this video. Oh, I love butterflies. Whatever experiments you like.
No butterflies were hurt in the making of this video.
I set them on a boat, and I compare them to the very same experiment set up on Earth. If the motion is truly inertial, the results of all those experiments will be the same. If the ball rolls down the inclined plane on the boat, it will do so on Earth as well. So because the laws of physics are the same in all inertial reference frames, so too must be all experiments. And if all experiments are the same in every reference frame, then there is no experiment you could ever do which determines which state of motion is absolute rest. Now you might say, look, I feel like I'm at rest. Absolutely, I'm at rest. I'm sitting on my couch watching this video. What more rest do you want? Oh, but come on, now you're not so at rest, are you? You're actually on a spinning orb. And that spinning orb is spinning around another orb, spinning around the center of the galaxy, and the galaxy is hurtling through space, and you're not at rest at all. You're actually in this incredibly complicated motion. The consequence of the principle of relativity is that no experiment can tell what absolute state of motion is. So in summary, the principle of relativity says the laws of physics are the same in all inertial frames of reference, and this implies that absolute motion can't appear in any law of physics, that all experiments run the same, no matter which inertial reference frame you're in, on the boat or on Earth, and that no experiment can possibly reveal the absolute motion of any observer. It's almost as if absolute motion doesn't exist. You learned the first principle of special relativity. Are you ready for the second? The second principle is called the light postulate, and it says the speed of light in a vacuum is the same in every inertial frame of reference. What is the speed of light anyway? It turns out it's fast, really fast, 186,000 miles per second fast. This means if you were to measure the speed of light on a train, no matter where it came from, you'd find it's going 186,000 miles per second. If you were to measure it off the train, also 186,000 miles per second. And now this is weird. This is really different. It's not like almost anything that you're familiar with. Here's an example. Let me go back to the motorway. If it weren't another car, but it were a beam of light going 186,000, suppose
The beam of light will be straight. It will just be slow, but it will be straight because the photon is a particle it has momentum. So that's not going to work. The laser beam will not bend under constant velocity. The only experiment I have left is the vertical particle accelerator. That's the only way of detection.
Suppose I were going 185,000. A person on the side of the road would say, wow, that's two really fast things going by. The light beam is traveling at 186,000 miles per second. And you, in this incredible spaceship, I know my spaceship is incredible, and according to the light postulates, although I'm traveling at just a hair less than the speed of light, I will still look at that same light beam and say that it's going 186,000 miles per second. That's strange. Most things are not like that. So if the light postulate is so weird, why do we believe it? Einstein didn't get these principles out of nowhere. He was looking at the most advanced theory of the time that was theory of electricity and magnetism, or electromagnetism. The theory of electromagnetism just worked if you made this assumption. You got all the right predictions about current flowing along wires, about the way that magnets work, about the way that magnets work when they're near electric wires. And after trying lots of different theories, this one with the light postulate turned out to be what worked. Einstein tried other things, but they didn't work. And this, it turns out, is the core of special relativity. The principle of relativity, that the laws of physics are the same in all inertial reference frames, and the light postulate, that the speed of light is the same no matter which inertial reference frame you're in. In the next lecture, we're going to see some of the really surprising things that these two principles imply. Thanks so much for coming, folks. I look forward to seeing you next time. You, spinning around the center of the galaxy, and the galaxy is hurtling through space, and you're not at rest at all. You're actually in this incredibly complicated motion. The consequence of the principle of relativity is that no experiment can tell what absolute state of motion is. So in summary, the principle of relativity says the laws of physics are the same in all inertial frames of reference.
Wow, that was brilliant. When he said that, I was thinking, wait, you could travel at incredible speeds, and what, you're going to start seeing things weird? That doesn't make any sense. Right, because light has momentum. So you can never tell that you're flying fast. I'm thinking about if you're moving fast through the ether, you're decaying slower relative to an observer. But we already know that. We can detect the ether. The only way to detect the ether is right now with a vertical particle accelerator. Did I start the paper how to detect the ether? Detecting the ether, correct. That might not work. So the vertical particle accelerating. Experiment how to detect the ether using a vertical particle accelerator. How to detect the ether using a vertical particle accelerator. The question is, what do we know about an interferometer? Will the interferometer fail? Will it fail? Will it go length contraction? So let's imagine an interferometer flying at no one has ever thought about this. Am I the first person to have to think about this? So this has to do with an interferometer. Interferometer length contraction. This was the video where I finally realized length contraction. It's not an illusion, but it's not real, which is really confusing. It's definitely very confusing. A simple experiment to prove that the Michelson-Morley experiment is not proof of length contraction. What?
Following the failure of the Michelson-Morley experiment to measure Earth's motion through space, many theories were proposed in an attempt to explain the unexpected results. The more prevalent theory today is that of length contraction effects. In this video, we'll see a novel use of the Sagnac interferometer to measure an observer's velocity in space. The interferometer was designed in a way that even if length contraction effects are present, the interferometer will still be able to produce a measurable result. The interferometer is not as efficient as a Michelson interferometer, requiring longer mirror distances, but it becomes very simple and practical for high velocities such as the solar system velocity within the Milky Way galaxy. In 1887, Albert Michelson and Edward Morley performed an experiment intended to measure Earth's motion through space. The interferometer was sensitive enough for measuring Earth's orbital velocity around the Sun. While there were minor changes in the interference pattern during the experiment, these were too small to be of any significance. The general conclusion is that no motion was detected. A brief discussion is presented here, as well as the prevalent explanation for the null result. A simplified version of the experimental setup is presented in this figure. An incoming light beam, A, is split into beams B and C.
So an incoming light A is split into B and C. What? I guess this is the splitter, B and C. The letter B repeats with A and B. Oh my god. Anyway, C. So this is impossible to understand. I don't know what's going on here.
These beams are reflected back as beams D and E and recombined into B.
D and E. E I understand. I don't get it. Why does this... What? Where did it go? Oh, A. This is A. Oh my god. So this is A. It went on to becoming B, then D, then F, where A became C, then E, then F.
Beam F, which forms an interference pattern. The expected fringe shift just on Earth's orbital velocity alone was expected to be about 0.4 fringes. Since no fringe changes were observed, the Lorentz-Fitzgerald length contraction effects hypothesis in the direction of motion became the more prevalent explanation, which was later incorporated into Einstein's special relativity. The length contraction factor is known as the Lorentz factor and represented by the Greek letter gamma. It is important to note that length contraction effects are used to explain that the times taken by the two beams to make the round trip are the same, and therefore the interference pattern does not change. While for geometric reasons we can deduce that the times for the vertical beams B and D are equal, this is not the case for the horizontal beams C and E. It is given that the outgoing beam C will take longer to reach mirror B than the incoming beam E takes to reach the beam splitter, but the sum of the times from both beams will be the same as the sum for the vertical beams. The purpose of this experiment is to compare one of the vertical beams with only one of the horizontal beams. Would the times be the same? If length contractions are the real explanation for the results of the Michelson-Morley experiment, then it is clear that the times for individual horizontal beams should not be the same. Based on Mr. Michelson's work and the work of others, an interferometer was developed that is capable of measuring an observer's velocity in space, even when length contraction effects are present. To make it easier to understand, the interferometer is simplified as a Mach-Zehnder type interferometer. In this configuration, the beams are split at the top right and recombined at the bottom left. The beams do not return to their source of origin.
So this is the light coming in. It splits in two. This is A. So, and this is B. and then they are recombined. So they both. So this guy first went down and then to the left, where this is the velocity. So this is the slow part. But what is this tube?
The asymmetry is introduced into the separate beams by placing a glass rod in the path of the bottom beam. The effective length of the interferometer becomes the length of the glass rod. All other paths have no significance. The time that it takes for light to move the length of the path is calculated as follows. For the beam labeled A, inside the glass rod we use Fresnel formula given that B is much less than C. For the beam labeled B we have this formula. When we rotate the fixture 90 degrees from vector B, then for beam A. For beam B we have this formula. From these equations we can determine delta T for L non-length contracted. And for a length contracted L. We can now solve for the expected number of fringe shifts as a function of B given L. The number of fringes is calculated with this formula. Shown in this table is the calculated number of fringes when a 0.44 meters glass rod is used. L is both length contracted and non-length contracted in the calculations. 3 different velocities are considered in the table in this order. Earth's orbital velocity around the sun. In this case, the interferometer would produce only 1/100th of a fringe, which is hard to observe. The solar system velocity around the Milky Way galaxy. This would produce more than half a fringe shift. This would be observable. The estimated solar system velocity relative to the CMB. The interferometer would produce about 2 fringe shift or better. While the operation of this interferometer is easy to understand, this is not the best way to do it. A Mach-Zehnder interferometer is very susceptible to vibration noise. The motion of any of the 4 mirrors will cause the interference pattern to change. The actual implementation uses a modified Sagnac interferometer. This is shown in this image. This is an equivalent interferometer, but much more stable and less sensitive to vibration noise. We'll let the viewer do the analysis and verify that the 2 interferometers are
I don't understand. This is not too long ago. Who is she? "17 videos."
What is gravity, and how does it work? This video will present a new way to explain gravitation. The intent is to find a model that is a better match for experimental data. While relativity considers motion to be an event between 2 objects, we are going to see that all motion is relative to space itself. The evidence is truly overwhelming. We're also going to see how Mr. Albert Michelson, known for the Michelson-Morley experiment, has already proven that the speed of light is not constant for all frames of reference, despite common beliefs to the contrary. We are going to see how anybody moving at a relativistic speed can just look out of the window of their vehicle and tell that they are moving very quickly. No need to look at the instrumentation or to do any experiment. We are also going to see that we are not the center of the universe, again, just in a different way. The viewer will need to have a basic understanding of special and general relativity to be able to follow the concepts presented. The viewer is encouraged to look at the many guides and videos about relativity that are available. While there is some math, it is kept at the high school algebra level for easier understanding. With that said, let's get started with the first section. In this section, we'll try to prove that objects move with respect to space itself, that time dilation effects are dependent on the observer's speed in space. This is not very difficult to prove, but it is not a popular concept in the scientific community. Just follow along. Corroborating evidence will be provided as we go. Let's start by quickly reviewing the concept of relative motion. Special relativity states that 2 observers in motion relative to each other
Sounds like she is introducing ether.
perceive each other as running on a slower clock than their own, and that they experience some length contraction in the direction of motion. Let's use a real-life example to better illustrate the case. By some estimates, 10,000 muons fall to every square meter of Earth's surface every minute.
Muons are created when cosmic rays strike molecules in the upper atmosphere. They have a very short life, about 2.2 microseconds. See this
She knows her stuff very well.
illustration for the path of a muon. Since muons are traveling very fast, near the speed of light, a muon experiences time dilation that allows it to travel much farther than the 660 meters that light would travel in 2.2 microseconds. Muons actually make it to Earth's surface and well below because they interact very little with other matter. That means that the life of a muon may be lengthened to about 500 microseconds. From the muon's perspective, Earth is moving at nearly the speed of light. Earth experiences length contraction and looks like a flat pancake. Earth's atmosphere is only a few hundred meters thick. A muon's 2.2 microsecond life is long enough for it to go through before it decays. These are logical sounding explanations from the perspectives of the muon and Earth as to how events unfold. Let's introduce a third element to this event. Say there is a pulsar some 1,000 light years away to act as a sort of clock. Let's have this pulsar send out a pulse every 100 microseconds. A real pulsar with a period that short cannot be found, but let's assume that one exists. Let's also have the muon's motion be perpendicular to the direction of the pulses. This will allow it to experience the same Doppler effect as Earth. Now, from the Earth's perspective, as the muon falls through the atmosphere, an Earth observer will see 5 pulses from the pulsar before the muon decays 500 microseconds later. From the muon's perspective, as it goes through Earth's atmosphere, it will also see 5 pulses in its 2.2 microsecond light. While Earth is seeing 100 microsecond pulses, the muon will see very short pulses of only 0.44 microseconds. It is clear that the Earth's clock and the muon's clock are not running at the same rate when it comes to measuring the pulsar period. They are experiencing different time dilation effects, and since their time dilation effects are due to their respective speeds, we have to ask, speeds relative to what? Let's have another muon 180 degrees from the first on the other side of Earth, also moving near the speed of light and with about the same life as the first. The second muon's path will also be as long as the first, and it will see the same short pulse periods as the first muon. There has to be a speed along the axis formed by the two muons for which the perceived period of the pulsar will be at a maximum. A spaceship moving with constant acceleration along this axis will also see shorter and shorter periods for the pulsar as it approaches the same frame of reference as either of the two muons. This graph shows the period of the pulsar as seen by an observer depending on his or her velocity in space. The graph uses Lorenz's transformation equation to calculate the pulsar period as seen by a moving observer. For an observer on Earth, where the motion is relatively small, the period of the pulsar is very close to the maximum. There are many other cases where time dilation also works asymmetrically. For example, atomic clocks in orbit in the space station are known to run slower than atomic clocks on the ground. In this case, both the observer on Earth and the space station observer concur that the clocks on the space station run slower. There are some claims that the reason is because the space station clock is in a periodic motion, a recurring event as the station orbits Earth. We will see later on how these explanations fall short. First, we need to lay some groundwork. We are going to take a small detour to clarify an issue that seems to confuse many. That is the direction of gravitational acceleration. This is the formula for gravity as provided by Newton, and that is familiar to most people. This formula is incomplete. As we know, accelerations are vectors, and gravitational acceleration is no exception. The formula must be written like this. Here, we have the left side of the equation as a vector. If the left side of the equation is a vector, then the right side should also be a vector. G is a constant, and mass has no direction. What about r? R indicates not only the distance from Earth's center to a point on the surface, but also a direction. Notice that the distance to Mount Everest and to Death Valley are not the same, and the direction is also different. Gravitational acceleration takes the direction of r, which is away from Earth. We should write the formula for gravitational acceleration like this. This may seem counterintuitive, as most people consider gravitational acceleration to be down, not up. Let's try to clarify this. Accelerations are measured.
Yeah, but you can't say vector squared. I don't think you can say that. Usually you use a unit vector r.
By instruments called accelerometers. This is an image of their internal structure. A heavy mass is placed between two plates made up of piezoelectric material. Piezoelectric materials have the property that they produce a voltage when they are subjected to pressure. If we were to push the accelerometer to the right, Newton's third law dictates that the heavy mass inertia would push back, resisting the motion. This would put pressure on the plate on the left, which would produce a voltage. The voltage on the left plate tells us that the acceleration is to the right. Similarly, if the accelerometer is pushed to the left, the plate on the right would be under pressure and produce a voltage. This would indicate that the acceleration is to the left. Let's now rotate the accelerometer and place it on the table. The accelerometer will be just resting on the table and not moving. Will it measure any acceleration? Well, yes. The weight of the heavy mass will apply pressure on the bottom plate, which will in turn produce an electric voltage, indicating that there is an upward acceleration. Why is this important? It is important for unmanned vehicles so they can determine their location. These are the formulas that unmanned vehicles use for calculating their present position. For the x and y axis, position is determined by their respective velocities and acceleration. For their z-axis position, which is altitude, they will subtract gravitational acceleration. This is also what relativity's equivalence principle is all about. An astronaut in an accelerating rocket will experience the same effects as a person on Earth's ground. For the astronaut, the acceleration is up. For the person on the ground, the acceleration is also up. If the astronaut had a ball in one hand and then let go of the ball would not accelerate to the floor. The floor would accelerate up to the ball. By far, the most widely cited proof for relative motion is the Michelson-Morley experiment. In this experiment, an interferometer is used to try to measure Earth's motion in space. This is a simplified version of the interferometer. Light entering in the lower left corner is split into two beams. They travel more or less an equal distance, L, and are reflected back to the origin to be combined, and form an interference pattern. This short animation shows the path taken by two photons as they travel the length of the two arms. The time that it takes for a photon to make a round trip is derived from these equations. L equals v times t. That means that t equals L over v. In this case, v is the speed of light. When the interferometer is in motion with the velocity of vm times t.
Wait, what was that?
This short equal distance, L, and are reflected back to the origin to be combined, and form an interference pattern. This short animation shows the path taken by two photons as they travel the length of the two arms. The time that it takes for a photon to make a round trip is derived from these equations. L equals v times t. That means that t equals L over v. In this case, v is the speed of light. When the interferometer is in motion with a velocity of vm, then the path that light follows is longer and takes a longer time. For the vertical arm, a full round trip, tv, is given by this formula. For the horizontal arm, th, the formula has two components, for the left to right and right to left trips. With a little algebra, we get these equations. For vm greater than 0, the time on the vertical arm will always be less than the time on the horizontal arm. When the interferometer is rotated, then the interference pattern will change as the two arms trade places. The Michelson-Morley experiment had arms with a length L of 11 meters, with enough sensitivity to measure Earth's orbital speed around the sun. Michelson and Morley were not able to detect any motion at all. They got a null result. This experiment has been repeated numerous times with identical results as seen in this chart. The null result is cited to validate relativity's premise that light is constant for all frames of reference. We'll come back to revisit this experiment and others later on and propose a different explanation for the result. We are now going to take a brief look at the operation of the GPS constellation. The GPS constellation of satellites has been called an ongoing relativity experiment that demonstrates general and special relativity time dilation effects. All GPS satellites send out a simultaneous pulse every second. A receiver on the ground receives pulses from a few satellites. By solving a set of equations with data provided by the satellites, the receiver can determine its location in 3D and time. For the system to work, the satellite clocks are kept synchronized with the master clock at the ground station, and all clocks must run at the same rate. If the clocks do not run at the same rate, then maintaining synchronization is not possible. Since the satellites are moving as they orbit Earth, they experience time dilation effects that are different than those for the ground station. We'll do a quick analysis of the time dilation present for satellites and the ground station. We'll look at just one satellite for simplicity. First, we'll determine the satellite orbital speed as it goes around Earth. This results in special relativity time dilation effects as given by this formula. The notation dilated time versus non-dilated time is used to make it easy to follow. We also have to consider gravitational time dilation effects due to Earth's presence. These are given by a similar formula, but it uses Earth's escape velocity. What is the direction of the escape velocity? Some scientists claim that the escape velocity is in any direction away from Earth, and that may very well work for escaping from Earth, but that is not what the math says. This is the formula for the escape velocity. It is derived by integrating the formula for gravitational acceleration. This r and this r are the same, therefore the escape velocity vector takes the same direction as the radius of the orbit to the satellite. We can now plot the vector for gravitational time dilations. Notice that this vector can also be interpreted as if the satellite were moving in a direction away from Earth, just like the orbiting motion. There is no change in the distance from the satellite to Earth. It is more of a pretend motion. Since the time dilation vectors are perpendicular to each other, we can use the Pythagorean theorem to calculate the total time dilations for the satellite. We also calculate the time dilations for the GPS ground station, following the same process, taking into account Earth's rotational speed. By doing these calculations, we can determine that the satellite and ground station do not experience the same time dilation effects. And if we used the same clock for the satellite and the ground station, they would diverge by 38 microseconds every 24 hours, which would result in an error in position of several miles. This is clearly not acceptable. GPS satellite clocks are designed to run a little bit slower on Earth, so they speed up and run at the same rate as the ground station's clock once they are in orbit. Let's take a closer look at gravitational time dilation vectors. What if this is not pretend motion? What if this is real motion? The satellite's distance to Earth is not changing if the satellite is experiencing vertical motion. And since all motion is relative to space itself, then we have to conclude that space is moving through the satellite. In this case, space is moving, that is, falling towards Earth. Let's look at the implications of this assumption. What we call gravitational time dilation becomes special relativity time dilation. It means that all time dilation is a consequence of motion through space. What we experience as gravitational acceleration effects are due to space accelerating through us as it falls to Earth and dragging all objects along with it. Scientists make a distinction between inertial mass and gravitational mass, where inertial mass is an object's resistance to being accelerated by force, and gravitational mass measures the gravitational force exerted by an object. With this assumption, there is no difference between the two. It is all inertial mass. The equivalence principle becomes an identity. There is no difference between a rocket accelerating through space and space accelerating through a stationary rocket on the ground. It also means that gravity is not a force of nature, which makes it compatible with quantum theory, and gravitons are not needed.
Gravitational time dilation. Gravitational time dilation becomes special relativity time dilation. All time dilations are consequences of motion through space. Gravitational acceleration effects are due to space accelerating. Gravitation are due to space accelerating through us as it falls to Earth. That's where she's getting it wrong. It's not accelerating, it's just flowing. It doesn't have to accelerate. She didn't think it through. There is no distinction between gravitational and inertial mass. How is this relevant?
Exerted by an object. With this assumption, there is no difference between the two. It is all inertial mass.
What?
The equivalence effects are due to space accelerating through us as it falls to Earth and dragging all objects along with it. Scientists make a distinction between inertial mass and gravitational mass, where inertial mass is an object's resistance to being accelerated by a force, and gravitational mass measures the gravitational force exerted by an object. With this assumption, there is no difference between the two. It is all.
How is this? Where is inertial? What? She didn't discuss inertial mass.
Inertial mass. The equivalence principle becomes an identity. There is no difference between a rocket accelerating through space and space accelerating through a stationary rocket on the ground. It also means that gravity is not a force of nature, which makes it compatible with quantum theory, and gravitons are not needed.
What?
The effect of space falling to Earth only extends to that area of space where Earth's gravitational field is dominant. This means that it would form a bubble around Earth. The bubble is similar to magnetic fields around a magnet. Far away from Earth, the sun's gravitational field would form a bubble around the whole solar system. This assumption is not without some problems, and they will be addressed later on. For now, let's see how this plays out. Let's go back to the GPS constellation. Let's say that we want to synchronize the GPS constellation with a satellite orbiting the sun in the same orbit as Earth. In this case, we would add time dilation vectors the same way that we did for the GPS satellites to determine the time dilation effect experienced by the satellite orbiting the sun. These vectors would be much larger, as the orbiting velocity and gravitational time dilation effects are also bigger. What do we do with the GPS satellites? Do we add the same vectors too? After all, the GPS satellites orbit the sun along with Earth. You can see how this would cause some serious problems. The GPS time dilation effects would not be constant, because the resulting magnitude of the vectors would not be constant. The GPS constellation would not be synchronized anymore and would result in positioning errors. We will pause here and return to address this situation at a later time.
I don't know.
If space is falling towards Earth, then the Michelson-Morley experiment should yield a null result, which it did. Our assumption matches the result of the experiment. Rotating the experimental setup left and right should have no impact on the results, and it didn't. Michelson was also part of another experiment known as the Michelson-Gale-Pearson experiment. This experiment was intended to measure Earth's rotational velocity at the surface. The setup is shown here. Light entering in corner A is split, with one beam going clockwise and the other one counterclockwise. Due to Earth's spherical shape, the rotational velocity is not the same for all latitudes, with latitudes closer to the poles rotating slower than latitudes closer to the equator. In the setup, light takes longer to go from left to right than it does from right to left. The difference is greater in the lower latitudes because of the higher velocities. The experiment included a bypass path very close to the starting point to be used as reference against the longer loop. The experiment was a success, and Earth's rotational velocity was measured with an accuracy of slightly greater than 2%. It speaks volumes of the genius of Mr. Michelson to continue doing experiments despite his previous results. He produced another way of measuring Earth's rotational velocity. This is the way we want science to work. Different methods giving us the same results. There is no disagreement between the different ways of measuring Earth's rotational velocity. The importance of this experiment is that it ties together time dilation effects due to motion with the results of an interferometer. The time dilation effects experienced by orbiting satellites can likewise be measured with an interferometer. It has been proposed that this setup is similar to the Sagnac interferometer. The Sagnac interferometer has a split beam going in opposite directions in a rectangle made up of mirrors. Light travels the same distance and it takes the same amount of time in either direction. When the setup is rotated, light circulating in the same direction as the rotation takes a longer time as it tries to catch up to the mirrors than the light in the opposite direction. This results in a change of the interference pattern. Most modern optical gyroscopes are based on this principle. Looking at the Michelson-Gale-Pearson experiment, you can see the similarities. Let's modify the setup such that the mirror on corner D will reflect the light back to corner A, and the mirror on corner F will also reflect the light back to corner A. We can take this whole section out. This is now the original Michelson-Morley configuration. It does not change the fact that light takes longer to go from A to F than from F back to A. You can see that the interferometer works as intended. It also tells us that the speed of light is not constant for all frames of reference. At the very least, this is an effect that should be considered when measuring the speed of light. The original Michelson-Morley experiment, with arms of only 11 meters, did not have enough sensitivity to measure the motion that was present. This is different from saying that there was none. Some scientists claim that the reason why this works is because objects on Earth's surface will follow a circular path as Earth rotates. This is not a good explanation. Earth's orbit around the sun is also somewhat circular, and so is the sun's orbit around the galaxy. A circle is a circle, regardless of the size of the diameter, and whether it takes 1 day, 1 year, or 230 million years to go around it, it is still a circle. If you have ever heard an explanation for relativity involving a train on Earth's circular surface, claiming that the speed of light is the same for all, let's just say that it's hard to see how we can reconcile that claim with this experiment. Let's go back to the original Michelson-Morley experiment, and let's run the experiment as Michelson and Morley did to measure Earth's motion in space. As we rotate their setup, the instrument is not detecting any motion. It reads a velocity equal to 0. If the velocity is 0, then the time dilation should also be 0. We use the Lorentz transformation equation to determine the time dilation, and there is none. Dilated time equals non-dilated time. We can now go back to the GPS constellation and remove vectors for the Earth's orbital motion and the sun's gravitational time dilation. They do not exist. For the GPS constellation, there is no time dilation due to Earth's orbit, nor solar gravitational time dilation, nor time dilation due to the sun's motion, nor the galaxy's motion. What the Michelson-Morley experiment tells us is not that the speed of light is constant for all frames of reference. What it tells us is that Earth's velocity through space as it goes around the sun is equal to 0. Earth's gravitational field creates a space bubble around Earth. The bubble moves around the sun. Inside the bubble, space moves toward Earth. Objects orbiting Earth will only experience time dilation due to their orbital velocity and due to space moving through them as it falls to Earth. Nothing else. If space is falling towards Earth, then the Michelson-Morley experiment should yield a null result, which it did. Our assumption matches the result of the experiment. Rotating the experimental setup
There it is. She has an arrow down.
left and right should have no impact on the results, and it didn't. Michelson was also part of another experiment known as the Michelson-Gale-Pearson experiment. This
Wait.
experiment was intended to measure Earth's rotational velocity at the surface. The setup is shown here.
Wait, I just listened to that. So now this 6.
Aberration is the apparent change in position of other objects from their true position due to the motion of the observer. This is the motion of the observer in space. It has nothing to do with the motion of the source or the relative motion of the source and observer. In this animation, we see a photon falling vertically. A moving telescope is placed at an angle to receive the photon. The path of the photon is this. The observer sees it here. The effect is observed from Earth for distant stars and for the Sun. Stars in the North Pole seem to be moving in a circle throughout the year. In this image, the blue line indicates the true position, the red line indicates the apparent position. From Earth, the effect is only consistent with Earth's orbital velocity around the Sun. The effect is very small, about 1% the size of the full moon. It may be small, but it is noticeable. Classical theory and relativity have different formulas for explaining the effect. With relativity,
How can I find her? No, where's Google? Is this Google? Oh, I didn't go to Google. Okay. How can I find her? Maybe on X?
An empty glass and tip in some water and food colouring. Then add some syrup or treacle. Then finally, fill the glass up with some oil and leave.
Well, this no.
Aberration is the apparent change in position of other objects from their true position due to the motion of the observer. This photon will move from one field in space into another and continue with its relative trajectory to the sun. The effect is very small, about 1% the size of the full moon. The path of the photon is this. The observer sees it here. The effect is observed from Earth for distant stars and for the sun. Stars in the North Pole seem to be moving in a circle throughout the year. In this image, the blue line indicates the true position, the red line indicates the apparent position. From Earth, the effect is only consistent with Earth's orbital velocity around the sun. The effect is very small, about 1% the size of the full moon. It may be small, but it is noticeable. Classical theory and relativity have different formulas for explaining the effect, with relativity adjusting the formula to maintain the speed of light as constant for the observer.
She never answers questions. There it is. She does 2 years ago. Who is she? How can I get in touch with her? The document in the description. How can I find her?
This chart shows the apparent position for a star at 90 degrees from the motion of the observer, as the observer's velocity increases. Notice that there is not much difference between classical theory and relativity until about 30% the speed of light. This other chart shows the apparent position of stars for an observer traveling at 90% the speed of light. The x-axis lists the real angular position with respect to the direction of travel, and the y-axis the apparent position. As Earth travels around the sun, photons falling to Earth will cross into Earth's space bubble. The motion is similar to a puck moving between two air hockey tables that are sliding past.
So Maxwell's equations predict or show that you can have traveling electromagnetic waves that travel at a speed that's equal to the speed of light. The speed of light had been measured independently at the time. It was known to be about 3 times 10 to the 8 meters per second. And light was also known to have wave-like properties. So other waves like sound waves, water waves exhibit phenomena such as diffraction, interference, and light exhibits the same phenomena. So the conclusion then is that Maxwell's equations predicted the speed of light. So again, the speed of light, the variable c, 3 times 10 to the 8 meters per second, that can be predicted in terms of other known physical constants, mu naught and epsilon naught. So this was an amazing result, helped settle the question of what light is, but it also led to all sorts of other questions. So Maxwell's equations predicts the speed of light, but the speed of light relative to what? Right? We always have to measure velocities relative to a reference frame. What's the reference frame we should use to measure the speed of light? Another way of thinking about this is what medium would carry a light wave? So let me say what I mean by this. So a water wave, those are disturbances in water, and so we say that the water propagates the wave. A water wave is a disturbance in water. Sound waves are propagated by molecules in the air. It's a compression wave. Molecules in the air get compressed and then elongated, and that pattern is sound, which we would then interpret. So what is the medium? What is the stuff that carries light waves? And this is weird. And moreover, light comes through essentially empty space to us, right? The sun comes through outer space, and then that light reaches us. What is it traveling through? So the answer to that question that physicists had in the 1800s was to say that light is propagated through the ether. So the ether is some unseen and undetectable medium that is responsible for carrying light waves. It sounds both a little naive and a little spooky now, the idea that there's some ether permeating everything, but we can't detect it, but it's the thing that makes light waves go. But that was what was generally believed in the 1800s. So light travels at the speed of light relative to the ether, this clear, odorless substance that permeates the universe that lets light waves travel. But as we'll see, the existence of the ether doesn't really, maybe it solves one problem, but it leads to some other even deeper problems. Let's use an example to help us think through this ether business a little bit more. So here's the scenario. Anastasia shoots a laser beam to the right, and a laser beam is a beam of light, so it travels at the speed of light. Beowulf, as is often the case, is on a train moving at speed beta, also to the right, and we want to know, what does Beowulf observe for the speed of the laser beam? All right. You might notice, by the way, that this is similar to an example that we did back in Unit 1, so we can approach it the same way. So here's our Galilean velocity transformation equation, and let's draw a picture. All right, so here's Anastasia on the ground, and here's a laser beam, I guess in orange. I kind of felt like a laser beam should be yellow, but yellow doesn't really show up. And the laser beam is going to travel at the speed of light, and we use the letter C to stand for the speed of light. All right. So here's Beowulf on his train. And Beowulf, the train is traveling at a speed of beta. All right, so we've done problems like this before. Let's see how this is going to work. So V, that's going to be C. All right, so V prime, that's the speed of the laser beam as observed by Beowulf. V is the speed of the laser beam as observed by Anastasia on the ground. And then we're going to do this. All right, so the picture here is that Anastasia on the ground is at rest with respect to the ether. So ether, which is the invisible medium through which this light wave travels, through which this laser beam travels, is at rest with respect to Anastasia. So Beowulf over here is moving a speed beta with respect to Anastasia and with respect to the ether. So what this means is that Beowulf will observe a speed of light that's equal to C minus beta. He'll observe a speed of light that's different than the speed of light that Anastasia observes, which is C. So this example seems innocent and straightforward, but it actually leads to a big puzzle. Here's the situation. So what we just saw was that Anastasia on the ground, with respect to the ether, observed light to travel at speed C, light speed. Beowulf observes a different light speed because Beowulf is moving at a speed beta. The Galilean transformation equations tell us that Beowulf observes light speed to be C minus beta. All right, so that seems fine. What could be wrong with that? Well, let's go back to the principle of relativity. Remember that says that the laws of physics are the same in all inertial reference frames. And we just learned about a new law of physics, Maxwell's equations. So Maxwell's equations are a law of physics, just like the conservation of energy, conservation of momentum, Newton's laws, and so on. So these are laws of physics. And these laws say that light travels at speed C. It doesn't say, the equations don't say anything about ether reference frames. Light travels at the speed C. Light travels at the speed of light. So that's what this...
The equations say relative to the ether. But you have to assume that whatever Anastasia's ether, the ether is basically at a constant speed relative to both Anastasia and Beowulf. So that can't play a role. So then it becomes a paradox. How could Beowulf measure a different speed of light?
This law of physics says, but that's not what happens here. Beowulf is observing light that's not traveling at speed C. So this is a puzzle. One of these statements has to be wrong. Either the statement of relativity is wrong, or something is wrong with how we figured this out. So this tension, this collision, is what's going to lead us to Einstein's formulation of relativity.
Mm-hmm. Okay, that's mainstream. There's nothing.
and asteroids in the solar system would also experience a delay proportional to their distance from the sun. The effect is illustrated in this animation. This is the sun's gravitational well. Only a cross-section of the well is shown for clarity. By the time light and gravity reach our planet, the sun has moved to a new position. The result is that the gravitational well is not symmetrical. This effect could be a serious problem for stable orbits. Let's look at the case of the moon orbiting Earth. By the time the moon returns to a given position 1 month later, Earth has changed direction of motion by 30 degrees as it moves around the sun. For objects farther away from the sun, the delay could be much greater to a given symmetrical the solar system amount of time. Since the sun is moving around the galaxy, Earth would orbit the location where the sun was 8.5 minutes ago. The rest of the planets and asteroids in the solar system would also experience a delay proportional to their distance from the sun. The effect is illustrated in this animation. This is the sun's gravitational well. Only a cross-section of the well is shown for clarity. By the time light and gravity reach our planet, the sun has moved to a new position. The result is that the gravitational well is not symmetrical. This effect could be a serious problem for stable orbits. Let's look at the case of the moon orbiting Earth. By the time the moon returns to a given position 1 month later, Earth has changed direction of motion by 30 degrees as it moves around the sun. For objects farther away from the sun, the delay could be much greater. For example, the Oort cloud is estimated to extend more than 1 light year from the sun. Scientists have known for some time that the planets orbit the instantaneous position of the sun, regardless of their distance. This would require that the speed of gravity be 10 billion times faster than the speed of light, or higher by some estimates. Recent observations of a merger between 2 neutron stars in August 2017 have confirmed that the speed of propagation of gravity is the same as the speed of light in a vacuum. This problem is easily resolved by having the sun be stationary in a gravitational bubble. When we look at Saturn, we aim our telescopes to the position where Saturn was over an hour ago, since it takes more than 1 hour for the light from Saturn to get to Earth. When we see Saturn, Saturn is no longer there. Let's suppose that Saturn were not moving, and it were always in the same position. If that were the case, we would see Saturn in its present location, even though light takes more than 1 hour to get to us. When the sun creates a gravitational bubble around itself, the sun is always at the center of the bubble. Space falls towards the sun within the bubble, and the sun's gravity propagates through the space in the bubble. Planets orbiting the sun within the sun's bubble will see the sun always in the same position, because the sun is not moving through space. The sun's bubble is moving through space, around the galaxy, carrying the planets, asteroids, comets, and all other objects orbiting the sun. This animation illustrates the effect. The planets also create smaller gravitational bubbles around themselves for their respective orbiting satellites. The planets are also stationary with respect to their own bubble. It is the planetary bubble that orbits the sun. Starting with this section, we try to address some of the issues that arise with the concept of space falling to Earth. The biggest question is, where does space go? As shown in this animation, we see that space accelerates as it falls to Earth. It moves faster as it gets closer to Earth, which is consistent with greater time dilation. Starting in the late 70s while studying the Big Bang, several scientists came to the conclusion that it was not the result of a big explosion, but rather the result of expansion of space. Space was expanding at some point, billions and billions of times faster than the speed of light. While space was expanding, it was taking matter along with it, at superluminal speeds. This was not an increase of the kinetic energy of the universe. The matter in expanding space was not moving with respect to space itself. If space is expandable, we might also presume that space is compressible. Within Earth's space bubble, new space is being sourced here at the edge of the bubble, while space is being compressed in this area here inside the bubble. Please note that there is no law for the conservation of space. Therefore, no current laws are being broken. Since space has no mass, no laws for the conservation of energy and momentum are being broken either at this point. Let's now consider a block of space as it falls to Earth. The speed at the bottom is faster than the speed at the top. The acceleration at the bottom is also faster than at the top. This would mean that space is expanding in a direction perpendicular to the Earth's surface, even as it is being compressed in a direction parallel to the surface. Here is a chart for the rate of vertical expansion of space as it falls to Earth. The compression is measured in meters per second, and the altitude is measured in kilometers. The scale is logarithmic for easier viewing. The chart plots the difference in escape velocities between 2 points, 1 kilometer in altitude apart. This effect has a very important impact on free-falling objects. Looking at this chart again, we see that the first light in the universe was formed around 380,000 years after the Big Bang. This light was in the visible region. Due to the expansion of space since then, this is now in the microwave region. It is called the cosmic microwave background radiation, and it is the subject of many studies. Let us start by considering 2 solid objects that are allowed to free fall to Earth from a distance of the moon's orbit. One object starts with an initial velocity of 0 meters per second relative to the ground, and the second object has a downward initial velocity of 2,880 meters per second. At that altitude, the escape velocity from Earth is 1,440 meters per second. This chart shows the difference from the escape velocity for the 2 objects as a function of their distance from Earth. Notice that the speed difference from the escape velocity continually decreases for both objects as they fall. Expanding space causes the objects to lose momentum as they fall, much like expanding space after the Big Bang turned visible light into microwave radiation. This is better illustrated with the following animation. In this example, we have a puck on an air hockey table. The puck is moving to the right at 5 meters per second with respect to the 0 line marker. The table has markers painted on it, labeled from 1 through 5, and they are 1 meter apart. But this is no ordinary table. This table is capable of stretching as if it were a rubber balloon and can increase in length. We will use the line label 0 as our reference point. The painted labels will move to the right at a velocity proportional to their distance. The 1 marker at 1 meter of distance will move at 1 meter per second. The 2 marker at 2 meters distance will move at 2 meters per second, and so on. We can use this formula to determine the position of the puck and the markers as a function of time. By setting the puck and marker formulas equal to each other, we can determine the time it will take for the puck to reach each marker. As we start the animation, we see that the puck reaches the 1 marker quickly, but then it takes longer and longer to reach the rest. The puck can never reach the 5 marker, as it is moving at the same speed. The important thing to notice here is that the puck is slowing down relative to the surface of the table. In this chart, we plot the velocity of the puck with respect to the surface of the table as a function of time, and we see an asymptotic velocity decline curve. The puck is still moving at 5 meters per second with respect to the 0 marker, and it has not experienced any acceleration, but the velocity with respect to the table surface is continuously declining. This is the same effect that galaxies experience with the expansion of space. The expansion of space is given by Hubble's constant. For photons, the expansion of space results in a change of wavelength. If the air hockey table were expanding with an acceleration component, then the puck would decelerate much more quickly. That is what we see in this chart of the 2 falling objects. As the expansion of space increases, the closer we get to the planet, the faster objects decelerate. The consequence of the loss of velocity in expanding space is a loss of momentum, resulting in lower time dilation effects. The loss of momentum effect has to also be present at the atomic and molecular levels. However, because the compression of space is greater for space falling to Earth, we can expect objects to experience a gain of molecular kinetic energy, expressed as a gain in temperature. This warming effect must also be present in our planet and on all celestial bodies. We can call it gravitational heating. We can also safely state that it has been constant for billions of years, and it is not a source of recent planetary warming. Since most matter is concentrated in areas of compressing space, and less so in areas of expanding space, the implication is that new energy is being created in the universe, and by extension, new mass, given the equivalence between energy and mass provided by relativity. We now turn our attention to what happens when an object crosses from one space bubble into another. Let's say, for instance, an asteroid enters Earth's bubble. What we observe is that there are no changes in the relative velocity between the asteroid and Earth other than gravitational effects. As the asteroid enters Earth's bubble, there is a change in momentum that can be calculated with the following figure. The initial momentum in the space bubble matter checks the momentum more quickly declining. This is the same effect that galaxies experience with the expansion of space. The expansion of space is given by Hubble's constant. For photons, the expansion of space results in a change of wavelength. If the air hockey table were expanding with an acceleration component, then the puck would decelerate much more quickly. That is what we see in this chart of the two falling objects. As the expansion of space increases, the closer we get to the planet, the faster objects decelerate. The consequence of the loss of velocity in expanding space is a loss of momentum, resulting in lower time dilation effects. The loss of momentum effect has to also be present at the atomic and molecular levels. However, because the compression of space is greater for space falling to Earth, we can expect objects to experience a gain of molecular kinetic energy, expressed as a gain in temperature. This warming effect must also be present in our planet and on all celestial bodies. We can call it gravitational heating. We can also safely state that it has been constant for billions of years, and it is not a source of recent planetary warming. Since most matter is concentrated in areas of compressing space, and less so in areas of expanding space, the implication is that new energy is being created in the universe, and by extension, new mass, given the equivalence between energy and mass provided by relativity. We now turn our attention to what happens when an object crosses from one space bubble into another. Let's say, for instance, an asteroid enters Earth's bubble. What we observe is that there are no changes in the relative velocity between the asteroid and Earth, other than gravitational effects. As the asteroid enters Earth's bubble, there is a change in momentum that can be calculated with the following figure. The initial momentum in the space bubble it comes from, minus the velocity of the space in the bubble it moves into at the point of crossing, minus the velocity of Earth's space bubble, multiplied by the rest mass. The edge of the space bubble is also where Doppler effects take place due to the change in momentum of photons. For non-relativistic velocities, the effects of the momentum change are not very noticeable, but they are more significant for relativistic velocities. Notice that the change of momentum for an object crossing a bubble boundary does not affect the overall momentum of the solar system. Conservation of momentum still holds. Over the last few minutes, we have shown that the speed of light is not constant for all observers. This also implies that the laws of physics are not the same for all frames of reference. This may only be evident at relativistic speeds. Length contraction effects are not needed, and they are more trouble than they're worth. They were invented to explain the Michelson-Morley experiment, which is the wrong explanation. This does not mean that all the many contributions of relativity go away. Relativity's formulas still apply, but now, instead of motion being relative between two objects, motion for all objects is relative to space. We also offered an explanation as to why objects fall and how gravity works, with a concept first proposed by Newton, a concept that is consistent with aberration of light and retardation effects, and that also shares many of the properties of relativity. While relativity tells us that objects orbiting Earth follow the curvature of space caused by our planet's mass, no amount of space curving is going to make an object fall. We have also determined that space behaves differently than previously thought. We have adopted an attitude that says, if it is important, it matters, and if it has no mass, it does not matter. Space begs to differ. This is a small listing of the laws of physics that we have developed, and that are a credit to those that postulated them, but they do not apply to space. These laws only apply to us. They only apply to matter. Space can and does move faster than the speed of light. Space can and does create new matter and energy. When space moves, it drags matter along with it, without experiencing any slowdown or drag, without a need for any energy or force. Energy and force are only needed to move matter with respect to space itself. We cannot apply to space the same laws that apply to matter. For space, matter is like color. It is not that space cannot exist without matter. It looks more like space created us, and matter is not the center of the universe. It's not clear why space behaves the way it does, but this is a subject that requires further study of our ever-expanding universe. Does time really slow down in relativity? One of the key concepts in relativity is time dilation. In this video, we'll explore what really happens.
All right. Wow. She is. I wish I could contact her. How can I? I don't know how to contact her. Let me skip to her last video.
Space is very much like the air. We know it is all around us, but we cannot see it, touch it, or smell it, but we know it is there. In this video, we are going to see how we can tell what space and air are doing even though we cannot see them. If we release a helium balloon, we see the balloon rise up in the air. This happens because the density of helium is lower than that of the air, and the balloon rises. That is only the vertical motion. Often we also see the balloon drift to the side. This happens because the air is moving. We don't see it moving, but with the balloon we can tell the direction and speed of the air. The velocity of the balloon is the same as the air. When we say that the air is moving, this is with respect to the ground. In relativity, motion is relative. Two objects in not see it, touch it, or smell it, but we know it is there. In this video, we are going to see how we can tell what space and air are doing even though we cannot see them. If we release a helium balloon, we see the balloon.
Maybe I can
Smell it,
trace.
but we know it is there. In this video, we are going to see how we can tell what space and air are doing even though we cannot see them. If we release a helium
If she made this video, then maybe I can trace where this video was made. There's hardly any information here. I think with Google Maps, it's possible to find this place.
helium balloon, we see the balloon rise up in the air. This happens because the density of helium is lower than that of the air, and the balloon rises. That is only the vertical motion. Often we also see the balloon drift to the side. This happens because the air is moving. We don't see it moving, but with the balloon we can tell the direction and speed of the air. The velocity of
What country is this? Is this the US?
the balloon is the same as the air. When we say that the air is moving, this is with respect to the ground. In relativity, motion is relative. Two objects in inertial frames of reference moving relative to each other each can claim that they are not moving, and that it is the other object that is in motion. That is not the case for accelerations. Accelerations are absolute. When the velocity between two objects is changing, at least one, or maybe both, is in an accelerated state. This is true even in relativity. In relativity, acceleration results in a change in the inertial frame of reference, and they are absolute. Determining which object is in an accelerated state is very easy. There are devices called accelerometers that measure accelerations. Accelerations are not relative to other objects, but are relative to space. If we have a ship in space, and we make the rest of the universe disappear, the ship can still tell if it is in an accelerated state. This acceleration is only relative to space itself, as there would be nothing else to reference. Accelerometers are widely used in industry. Your cell phone has an accelerometer to determine which way is up. That's why the image rotates when you rotate your phone. Cars use accelerometers to deploy airbags in the event of a crash. They detect the acceleration of an impact. They are used in active suspension systems to smooth out a car's ride. If we attach an accelerometer to a steel pipe and then have a magnet approach the pipe, as the magnet pulls on the pipe, the accelerometer will measure the change in velocity as the pipe moves towards the magnet. Now let's see what happens when we drop the pipe from a tall building. As we know, the pipe will fall to the ground following Newton's gravity law. As the pipe falls, its velocity relative to the ground will be increasing. But here's the kicker. The accelerometer measures no accelerations. This is not a malfunction. The accelerometer tells us that its velocity relative to space is constant. How can this be? How can the velocity relative to the ground be increasing, but the velocity relative to space remain constant? The only explanation is that space is accelerating towards the ground at the same rate as the pipe. This is what gravity is. The accelerometer is only following Newton's first law that says that a body in motion tends to remain in motion. It follows space to the ground. There is no other explanation for it. If we use relativity's terminology, it defines an inertial frame of reference as a state where the velocity relative to space is constant. When we drop the accelerometer, its inertial frame of reference is accelerating towards the ground. Think about this. An inertial frame of reference accelerating to the ground. It also points to space accelerating to the ground. This is the reason why two falling objects of different mass released at the same time fall at the same rate. Neither can get ahead of the other if their inertial frame of reference is the same. In Newtonian mechanics, force equals mass times acceleration. Since gravitational motion does not create accelerations, the force is equal to zero, and gravity is not a force of nature. Theories that treat gravity as a force of nature are destined to fail. Accelerometers do not tell us the velocity of space, but we can determine the velocity of space by the time dilations that it causes. These are given by Schwarzschild formula for gravitational time dilations. It uses the escape velocity in the Lorentz factor. This is the formula used to calculate gravitational time dilations on Earth for GPS. Essentially, gravitational time dilations are just special relativity effects. As space moves around,
Schwarzschild developed gravitational time dilation?
us, as it falls to Earth. When Newton saw an apple fall from a tree, he derived Newtonian gravity. Einstein's thought experiment sees a man fall from a building that does not feel his own weight. He went on to derive general relativity. In this video, we combine Newtonian gravitational accelerations with Einstein's inertial state of falling bodies to derive a new model for gravity, where space falls to Earth at the escape velocity. The behavior of free-falling accelerometers gives us compelling evidence of this. More evidence will be available when an upcoming NASA mission launches the Deep Space Atomic Clock 2, as this clock would be expected to slow down when it moves out of Earth's gravitational field. The first question that we have to address is, what is energy? How do we define energy? Well, you may have heard of nuclear energy, electric energy, solar energy, and so on. There is only one type of energy in the astrophysics universe, and that is kinetic energy. All these other forms of energy are just different ways to get molecules moving. Just like Maxwell brought together electricity and magnetism, Einstein's formula brings together energy and mass. These two were previously considered to be separate items. In this video, we'll see how energy is actually mass. In fact, Einstein in his original paper described mass as a function of energy over the speed of light squared. Let's illustrate how this formula works. Let's say, for instance, that we have 100 kilograms mass at rest, and that we apply a force to it until it reaches a velocity of 1/10 the speed of light. Einstein tells us that the change in velocity will result in a change in inertial mass. We'll do the calculations here to see how that works. The mass increase is given by the Lorentz factor. We multiply the rest mass by gamma to determine the moving inertial mass. We'll call it m prime. The Lorentz factor is 1 over the square root of 1 minus b squared, divided by c squared. We'll rewrite it like this, and given that b is much less than c, we'll use the binomial expansion method to get the result. The binomial expansion method tells us that we write the first term, 1. The exponent, minus 1/2, multiplied by the second term to the power of 1. The following terms in the expansion will see increasing exponents, which, in the case of small v relative to the speed of light, get rapidly small. In this case, we get a good approximation with only the first two terms of the expansion. We can now get the value of m prime by multiplying the rest mass by the Lorentz factor. Solving for v equals 1/10 the speed of light tells us that gamma is approximately 1.005. The value of m prime is 100.5 kilograms. Now let's try to determine the amount of energy used to get the mass to this speed. From Newton we know that force equals mass times acceleration. Energy is equal to force times distance. In other words, energy is mass times acceleration times distance. Distance is equal to initial distance plus initial velocity multiplied by time plus 1/2 acceleration multiplied by time squared. We'll assume that the initial distance and initial velocity are 0. Velocity is equal to acceleration multiplied by time. We can express time as velocity over acceleration. Now we can calculate energy as the product of mass times acceleration times distance. Distance is 1/2 acceleration multiplied by time squared. We substitute time by velocity over acceleration and we have this expression. The a's cancel out and we replace v by 0.1 c. Solving for energy, we get that this is 1/2 kilogram multiplied by c squared. This is the amount of kinetic energy that was added to the 100 kilograms mass to get it to a velocity 1/10 the speed of light. Einstein's formula tells us that energy has mass. When we increase the kinetic energy of the 100 kilogram mass, the mass of this energy is added to the rest mass to get the total inertial mass. This is the reason for the mass increase over rest mass. We made a small mistake by holding the 100 kilogram mass constant in this multiplication. The mass will start increasing as soon as it starts moving. But the error in this case is less than 1%, and it equals all the discarded terms in the binomial expansion. The correct way to do it would be using calculus, but this approximation is good enough for illustration purposes. For the rest of this video, we will call the increase over the rest mass kinetic mass, to indicate mass gain due to the velocity of the rest mass. It is important to note that kinetic mass has the same properties as rest mass, such as weight, inertia, and gravitational field, except that, as we are going to see shortly, kinetic mass can be transferred to other objects by the collision with rest mass. Now let's look at how we get energy. Let's consider, for instance, what happens when we combine hydrogen molecules with oxygen molecules. From chemistry, we know that this will produce water, but this is not all. When we combine 2 moles of hydrogen with a mole of oxygen, we get a mole of water plus 280,000 joules of energy. But what is the form of this energy? What is it? The real process is that this energy release is the result of that the rest mass of water is less than the rest mass of the hydrogen and oxygen that we started with, about 3 nanograms less. The energy content of the water is expressed as the molecular velocity gained by the water molecules. We call this heat. That is why we produce water vapor, not liquid water. The total mass is still the same that we started. In this video, we are going to see how GPS clocks work. These are a new type of clock that has been developed in the last couple of decades. A clock is a device used to measure time. In the old days, these devices operated independently and were designed to run at a constant rate. Regardless of the technology used, be it a winding clock, a quartz clock, or even an atomic clock, they were all doing the same thing, ticking away based on an internal mechanism designed to maintain a constant rate. When you hear that in relativity, clocks do not tick at the same rate for all observers, they refer to this type of clock. If you have heard that you cannot do any experiment to measure your velocity in space, well, that is not correct. There are ways that you can use to measure your space velocity. They were pioneered by Mr. Albert Michelson. In this video, we'll show how interferometers that are being used every day tell us how to measure our space velocity. Following the Michelson-Morley experiment's failure to measure Earth's motion in space around the sun, and with the development of Einstein's relativity, it was assumed that all motion is relative, and it is not possible to measure motion through space. In this video, we are going to put this belief to rest. In addition to Michelson interferometers, there is another type of interferometer that can be used to measure motion. This is a Sagnac interferometer. This type of interferometer is widely used in the commercial world, mostly for measuring angular rotation in optical gyroscopes. We are going to see how this interferometer actually measures displacement velocity and how this translates into angular measurements. Let's first have a good understanding of how Sagnac interferometers work. Let's assume that we have a beam of light traveling in a circular disk, as the figure shown here. Half the beam goes clockwise, and the other half counterclockwise from a starting point S. If the disk of radius r is rotating with an angular velocity omega, the optical path difference is given by the following calculations. For the beam traveling clockwise, the distance traveled is given by this formula. The length of the circumference, 2 pi r, plus the tangential velocity, in this case r times omega, multiplied by the time clockwise. This is also equal to the speed of light multiplied by the time clockwise. For the beam traveling counterclockwise, the distance traveled is given by a similar formula. The length of the circumference minus the tangential velocity, multiplied by the time counterclockwise. This is also equal to the speed of light multiplied by the time counterclockwise. The time difference between the two beams to get back to the same point is derived by doing some algebra. C's cancel out. We also eliminate r omega squared, since this number is very small compared with c squared. We are left with 2 pi r times 2 r omega divided by c squared. We further simplify to this. This is the time difference for the two beams to come to the same place in the disk. By joining the two beams, we create an interference pattern that can tell us the angular and tangential velocities. Most uses involve measuring angular velocities in optical gyroscopes. The implementation of the disk is generally accomplished by means of a fiber optic cable. By a quirk of nature, the formula for the time difference between the two beams is the same. We'll let the viewer do the calculations. Just note that the speed of photons inside a fiber optic line has to be replaced by Fresnel formulas for the velocity of light in a moving medium. This will work for tangential velocities much smaller than the speed of light. If you do the algebra and do the same approximations as before, you should get the same formula. The important thing to note here is that there are no limits to the size of the radius. For example, a long optical fiber line that follows the orbit of a satellite can tell us how fast the satellite is moving in space around Earth. We could also send a long optical line all the way on Earth's orbital path around the sun to measure Earth's orbital velocity. We would need to wait about an hour to be able to get a measurement, but there is no reason to think that this would not work. We don't need to worry about pesky length contraction effects either, as these have never been an issue with optical gyroscopes. But as you can see, these are not very practical ways to measure velocities in space. Some people think that Sagnac interferometers can only be used to measure angular velocities, but that is not the case. Let's assume, for instance, that we add a second loop to the disk with a larger radius. When we rotate the disk, the angular velocity will be the same for both loops, but the tangential velocities will be different. This will result in interference patterns that are different for each loop. Mr. Michelson's genius was that he realized that we don't need to go all the way around an object to be able to make a measurement. Since the tangential velocities of the two rings are different, we just need to compare a small section of the two rings to be able to determine the angular velocity. This is what he did with the Michelson-Gale-Pearson experiment, where Earth's rotational velocity was measured to an accuracy of about 2%. If we wanted, for example, to use interferometry to measure the space station's orbital speed around Earth, we would need a single optical fiber line around the station. Again, there is no reason to think that this would not work. This interferometer works every day in commercial products, but this is the hard way to do it. A small rectangle with sides of 25 centimeters and a few hundred turns of optical fiber could do the same. But this is not necessary. We already know the method works, and we already know the station's orbital speed. Interferometry does not produce a very accurate measurement either. At best, we would get two significant figures. Radar is a better method for measuring the station's orbital speed with high accuracy and low risk. Optical gyroscopes are built with hundreds if not thousands of turns to get an accurate measurement. They are tested by measuring Earth's rotational velocity. In effect, a repeat of Michelson-Gale-Pearson experiment. But does this work when measuring velocities that are not going in circles? Actually, yes. A team at St. Cloud State University in Minnesota performed various experiments in 2003 using different shapes of Sagnac interferometers, and what they found was that if the length of the loop and the displacement velocity are the same, then the interference pattern is also the same. This is regardless of the angular velocity of the rollers or the area enclosed by the fiber. We can recompose the formula derived earlier to be expressed as the length of the path and the velocity of the displacement. This means that in theory, you could create any round-trip shape, elliptical, triangle, or even a 3D shape, and still measure your space velocity. You don't have to take a round trip either. You could only travel a small segment of the loop. It is important to note that you can only measure a targeted path. For example, if we place a loop on the moon's orbit around Earth, we would measure the moon's orbital velocity, but that would not include the moon's velocity around the sun. We would need a different loop for that. So what good is it to measure our velocity relative to space? Not much, really. If we have a ship traveling
traveling to Mars, the velocity relative to space is irrelevant. The only thing that matters is the velocity relative to Mars. This will tell us how long before it arrives, and to adjust the velocity so that it does not overshoot when it gets there. This is the same as an airplane flying to its destination. So if someone tells you that you cannot measure your velocity relative to space using interferometry, now you have something to talk about.
Why is there no way to talk to her? Usually there's like an email. She says that her gravity is based on Newton.
In this section, over the last few minutes,
If it has no mass, it doesn't matter. She never used the word. Oh, did she ever use the word ether? Wait, this is hers?
This may come as a surprise to many people, but there are in fact two special relativities that closely resemble each other.
Wait. This is the same channel, but why people get confused when studying relativity is easier when you see. Well, why didn't I?
And many people have problems telling them apart. In this video, we'll try to clarify the difference between the official theory of special relativity that everybody talks about and the experimental relativity that confuses many people. When Einstein developed his theory of relativity, it was meant to apply to rectilinear inertial motion, and the mathematical proofs and explanations depend on this. In our world on Earth, we are in circular motion as Earth rotates, and things work differently here. Let's start by looking at the basics. Here's a chart for the two relativities. The basic premise of relativity is that the speed of light is constant in all rectilinear inertial frames of reference. This is not true in circular motion frames of reference. Consider a Sagnac interferometer as shown here. A beam of light is split in two, with one beam going clockwise and the other going counterclockwise. The beams are recombined at the starting point to create an interference pattern. When the interferometer is rotated, the times that the beams take to go around the loop are different, and the interference pattern changes. This tells us that the speed of light for a rotating frame of reference is not the same in both directions. We can extend this concept to larger rotating bodies, such as Earth. Because Earth is rotating, the time that it takes for light to go between 2 points along the direction of rotation is not the same for one wave versus the other. Mr. Albert Michelson proved this with the Michelson-Gale-Pearson experiment, where he determined Earth's surface velocity with a Sagnac interferometer. Another concept of special relativity is time dilation effects. For rectilinear motion, time dilations are relative. In this image, for example, each observer sees his own clock running faster than the other guy's clock. They don't agree on whose clock is running faster. In circular motion, on the other hand, this disagreement does not exist. Atomic clocks in the space station run slower than atomic clocks on the ground due to the space station's high orbital speed compared to the ground's speed. The ground completes one revolution every 24 hours, while the space station completes one orbit every 90 minutes. The space station observer and the ground observer both agree that the ground clock runs faster than the space station clock. Length contractions are also a fundamental concept in rectilinear relativity. These are needed to keep the speed of light constant for all reference frames. Length contractions are also relative. Each observer sees the others being length contracted. In circular motion relativity, this concept is not addressed, and despite the results of the Michelson-Morley experiment, length contraction effects are never taken into account when Sagnac interferometers are used. Mass increase is another area of disagreement similar to time dilations, where rectilinear relativity tells us that two observers moving with respect to each other disagree on whose mass has been increased, while for circular motion there is no disagreement on who is moving faster and whose mass has been increased, as in the case of time dilations. Non-simultaneity of events is another important concept in relativity, where rectilinear relativity considers that two observers disagree on the timing of events separated by distance. This is what also keeps the speed of light constant for all frames of reference. In circular motion relativity, this is not the case. Because the speed of light is not constant in all directions, both observers agree in the timing of events. This is why GPS timing is the same for all points on Earth and all near-Earth frames of reference. The most important difference is that in rectilinear relativity, all motion is relative. There is no preferred inertial frame of reference. That's the reason why it's called relativity. In rotating frames of reference, all motion is absolute. Velocities are well defined. We know exactly the speed of the space station as it goes around Earth. We know Earth's rotational velocity and its velocity around the sun. There's nothing relative about it. This was demonstrated in Principia with Newton's bucket. So why haven't you heard of two relativities before? The reason is because rectilinear inertial motion relativity is very well defined. We have all the math, concepts, and explanations that have been developed over the years, which you can easily find material on, but it has one serious flaw. It only consists of mathematical proofs, algebraic formulas, and equations. There's no experimental evidence for it, no experimental observations that time dilations, length contractions, and mass increases are relative. In our galaxy, rectilinear inertial motion does not exist. All motion is circular. Planets orbit the sun in circles, they rotate in circles, the moon moves around in circles, the sun and stars go in circles around the galaxy, and so on. You cannot escape the effects of gravity. Circular motion relativity, on the other hand, does not have a well-defined theory, and it borrows pieces as needed from the rectilinear theory. Circular motion relativity is mostly made up of experimental observations, because a rotating Earth is the only frame of reference we have. Mainstream scientists don't even acknowledge that it exists as a separate theory. They consider it a special case, but this is the one everybody works with. It should be no surprise then that all explanations for relativity concentrate in the rectilinear theory. This is what they teach in schools. To make up for the lack of experimental evidence, they borrow data from the circular motion relativity, for example, claiming that the GPS proves relativity right, overlooking the fact that the GPS time dilations are not relative, and therefore contradict relativity. To make matters worse, many explanations for relativity use concepts that try to appeal to the familiar for the viewer. You see trains, cars, and people on the ground without realizing that Earth is a rotating frame of reference, and that the explanations, as stated, do not work. So when you hear some people claiming that the speed of light is not constant and Einstein is wrong, or that the time dilation in the Hafele-Keating experiment showed that Einstein is right, this is just people looking at the wrong side of a chart they don't know exists.
All right, let me log out of Discord. All right, I'm gonna go. Bye.